Hello all, I welcome you back onto this channel, and we hope that you have enjoyed the first video on this one-shot series of engineering mathematics that was on linear algebra. And also we expect that that video might have definitely boosted your some knowledge in linear algebra and might have given you some confidence even to solve some gate PYQs. Okay, and coming to the second module of this one-shot series, basic calculus. And many of you have asked in the comment section of the first linear algebra video that are we going to cover the complete syllabus of engineering mathematics? Yes, we are going to cover the complete syllabus of engineering mathematics. You are going to get every module like this in single shot, so that after some 8 to 9 lectures from us, definitely you will have complete command over the syllabus. Okay, so this basic calculus, if you see, one of my favorite chapters actually, and definitely if you see, this basic calculus is a strong foundation for many of the technical subjects that we deal with. Okay, for example, you take any of your core subjects, you have differentiations, integrations, then after solving differential equations, and this basic calculus is one very basic chapter and very strong foundation for the upcoming chapters like differential equations, vector calculus, or you say complex calculus, or some integrations in probability, all these things. Okay, so that's how this basic calculus is basically, majority it's developed by Sir Isaac Newton, and this basic calculus involves some of the very inceptional, I mean the fundamental theorems of the general physics. Okay, so without any delay, let us start this module. So before starting this module, I would like to give you some quick review of the topics that I'm going to cover. So basically, anyhow, I'm going to divide this lecture basically into three parts. First part, differential equations, differential calculus of single variable, then integral calculus of single variable, and finally I'm going to review of some multivariable calculus also. Okay, like limits, maxima minima concepts in 2 variables, 3 variables, we'll deal all these things. Okay, so once we are done with that, and this is basically that I'm going to cover in differential calculus, and this is basically integral calculus, and this is I'll talk about some multivariables calculus in this video. Okay, so without any delay, let us start the sessions. So first, why we need to build these fundamentals? Because we have seen it's quite often that we deal with differential equations, correct, in our day-to-day physics. As I told you in the first or generally I say, if you see, let us suppose if you have any block, for example. Okay, let us suppose I'm giving some simple class 12 level example, class 11 level. So let us suppose if this is a block, on this block you are applying some force F. Okay, so you have applied a force F on this block M, for example. Then what happens? Obviously the physics that we can understand is when you apply certain force on a mass M, this mass will accelerate, correct? So this block will try to move with certain acceleration. So this is the physics that's happening. So there is a block, you're pushing it, the block is moving. Now if you want to understand, or if I ask you this question, let us suppose initially at time t equal to 0, means initially this block is at rest, then after what time this block will have a velocity of 2 meters per second. If I ask you this question, for example, okay, you know that this block starts from rest and it accelerates. Now if I ask you this question, after what time this block will have 2 meters per second, for example, let us say. So now just by looking at this physics, you cannot answer this question, correct? You need to do some mathematical calculations. So basically every physical phenomena has to be converted to some mathematical equations for our understanding. So similarly, we will come to know that F is equal to m into dv by dt. So mass into acceleration, and acceleration is nothing but a rate of change of velocity. So now if you see, you will come to know that this is a differential equation, correct? So not only this, like this in many situations we generally come across many parts of calculus actually, and differential equations is one very important domain of calculus actually. Okay, now to solve differential equations, let us suppose you ended up with a differential equation, for example, differential equation. Okay, so to solve this differential equation, definitely you should know integration, correct? Because if you want to solve some differential equations, then definitely you should know what are the integrals of some functions. Okay, so to solve differential equations, we have to know something on this integration. Now if you want to talk something about integration, then definitely should know what is differentiation, correct? Because if I ask you what is integral of sin x, your answer is minus cos x, because you know that differentiation of cos x is minus sin x, correct? So that's why, anyhow, we'll see how those things are coming. So in integration, if you want to talk about integration, you need to know what is differentiation. Means basically you should know what is a derivative. So once you know what is differentiation, means basically if you want to know what is differentiation, actually you need to know two very important concepts which are called continuity and limits. Continuity, and of course for knowing continuity you should know what is a limit. Now to know what is a limit, basically, okay, we need to know one very important concept which is called neighborhood. Neighborhood. Okay, so we will start our discussion from this point, neighborhood. Okay, so eventually we'll go till this part in this module, and we'll have a separate module for differential equations, because that's quite a big domain in mathematics. So that's why if you see, we'll take the this in this module we'll take here, so that once acquiring knowledge of all these 5 or 6, you can say, subtopics, we will get to know how to solve this differential equation. Okay, so basically we'll start this module by understanding what is a neighborhood. Okay, now before I speak something about neighborhood, I'll ask you something. Look, let us suppose I'm writing some 4-5 steps here basically, and I'll ask you to identify what is the wrong step. Okay, you can pause the video and you can try to attempt. Look, for example, let A is equal to B. Okay, let us suppose I'm writing that let A is equal to B. For example, there are two numbers, I'm taking them equal. So whenever they are equal, I can write AB is equal to B square. I can write this. If AB is equal to B square, I can write A square minus AB is equal to A square minus B square. Correct? I can write, because if AB and B square both are same, then if I subtract AB from A square, or if I subtract B square from A square, both are same. Correct? So now let us suppose I am taking A common and I write A minus B. Here also I am factorizing A minus B into A plus B. Okay, so now if you see, I am cancelling the common factor A minus B. So A is equal to A plus B. This is what we have. Okay, now since A is equal to B, I am substituting this B as A basically. Okay, so A is equal to A plus, since B is same as A, I am replacing this. So you will get 1 is equal to 2 basically. Okay, but of course this result is pretty much wrong. So definitely I might have considered or I might have committed one mistake in out of these 6 to 7 steps. Okay, so what is the mistake that I have committed? Okay, so I request you to pause the video for a while and answer this question. Okay, now if you see, the mistake that I have committed here is, look, the mistake that I have committed here is this, is basically in this step. The mistake that I have committed is basically in this step. So what is the mistake I have committed? Look, whenever A is exactly equal to B, A minus B is actually 0. Okay, so I cannot cancel two zeros. Correct? Because what happens if I cancel two zeros? I can write 2 into 0 is equal to 3 into 0. And I can cancel 0 and 0, I can write 2 is equal to 3. But this is wrong actually. Correct? So that's the reason two zeros cannot be cancelled. But actually I have cancelled two zeros here. Cancellation of 0 on both sides. Cancellation of 0 on both sides actually gave me this result, which is not very certain to see in mathematics. But I'll tell you something. You all have done this example, that let us suppose if I write this x tends to 2, x square minus 4 by x minus 2. Let us suppose if I write this, limit x tends to 2, you will factorize this as x minus 2 into x plus 2 divided by x minus 2. Now what you will do? You will cancel this x minus 2 and x minus 2. Then you will get this result, limit x tends to 2, x plus 2, which you will write as 4. Correct? You have done this calculation. Of course, I will tell you why this is coming and all. Don't worry. If some of you are from +1 or 10th class level, don't worry. I will tell you what is this. Okay. Now, first thing, one thing is very clear, that two zeros cannot be cancelled. Okay, two zeros cannot be cancelled. So you have cancelled these two, which means one thing is very clear. When two zeros cannot be cancelled, but still you are cancelling these two, that means x minus 2 is not equal to 0. This much you know. Now this means x is not equal to 2. Okay, fine. X is not equal to 2. Then why are you substituting x equal to 2 again here? Tell me. Here, till this step, you decided, you are very strong, your mind is very clear that this x is not equal to 2. Good. Then why you are substituting again x equal to 2? So this is why you should know the concept of neighborhood actually, and the definition of limit. Okay, so here there is very much difference between x tends to 2 and x equal to 2. Okay, so both are not same actually here. So that's why if you see, we have to study the concept of neighborhood, and in neighborhood we will come to know what is this meaning of x tends to 2. Okay, let us see what happens. Okay, neighborhood of a, neighborhood of a, neighborhood of a, neighborhood of a. Okay, now see here, let us suppose I'll ask you some simple thing. For example, let us suppose you have a road like this, and let us suppose this is your home, for example. Okay, this is your home, for example. My name is Vinay, so let us call V. So this is your home. So then what happens? The people who are immediately next to us are called neighbors of us, correct? Similarly, someone who is here is also neighbors, but someone who is very far away, he is not a neighbor. You know this, correct? Now let us suppose you have some function in your home. Then what you will do, you will call certain people as neighbors depending upon your closeness with them, or depending upon the budget for the function. So depending on certain parameters, you decide some limit, some range up to which you should call them for the function, correct? Similarly, if this is my x-axis, let us say, then if you have a real number a, then definitely there could be some real numbers which are very close to a, correct? A minus 1 will be here somewhere very far away. A minus 1 is not a neighbor of a, because you know, between any two real numbers there are infinitely many real numbers. So that's why these two are very far away. Similarly, a plus 1 is also somewhere far away, but there are some real numbers which are very close to this a, correct? So let us suppose if I divide this, if I write this value of x as a minus delta, means assuming this space is delta, this space is delta, and similarly this value as a plus delta, then you can observe one thing. If I write x belongs to a minus delta comma a plus delta, where delta is some positive number but very small, okay, where delta is greater than 0 but delta is very small, okay, very small. So where delta greater than 0 is called neighborhood of a, neighborhood of a within delta limits, within delta limits, within delta limits. Okay, so why I'm writing delta limits? Because if I change this length of delta, or if I change the value of delta, then definitely the interval increases or decreases depending upon the variation of delta. Okay, so this is called neighborhood of delta. So when I write x tends to a, the meaning is x is in the neighborhood of a and it is moving towards a. That's the meaning of this. Okay, so when I say, if I say x tends to a, if x tends to a, this is read as x tends to a basically. Okay, so x tends to a, then this implies x is in neighborhood of a, x is in neighborhood of a, x is in neighborhood of a, and it is moving towards a, and it is moving towards, it is moving towards a. This is the meaning of neighborhood basically. Okay, or x tends to a basically. Now there is something called deleted neighborhood. Okay, so what is this deleted neighborhood? So deleted neighborhood, if I write in a simple sentence, deleted neighborhood is nothing but, deleted neighborhood is nothing but x belongs to a minus delta comma a plus delta minus a. So from this interval, when I write this interval a minus delta to a plus delta, then definitely you know there are infinitely many real numbers in between these two values, and also a is also coming in between this interval. But when I say deleted, a is actually skipped out of the interval. Okay, so a is not there in the interval, and limits are defined on deleted neighborhood actually. Okay, that's why you'll never substitute, means basically you never mean that x is actually equal to a, but x is lying somewhere in between a minus delta to a plus delta. Okay, now let us see the definition of limit. What is a limit actually? Okay, look, for example, many of you might be doing this simple things like SFDs, BMDs. For example, you take strength of materials, for example. Okay, some of could understand this. Look, I'll tell you, let us suppose I have a beam, for example. I have a beam like this, for example. Okay, I have a beam like this. It is fixed. Let us suppose it is fixed. Now let us suppose I am putting some loads on this, for example, for fun. I am putting some load here, some load here. Okay, some load here. Let us suppose like this. Now let us suppose this is 20 kilonewton, this is 30 kilonewton, and this is 40 kilonewton, let us say, for example. Okay, now let us suppose I am drawing the SFD of this beam, shear force diagram basically. Okay, so if I draw the SFD of this beam, how does it look like? It looks something like this. Okay, now let us suppose if this is your zero shear axis, for example. Now if I draw the SFD, it looks something like this, correct? So basically you have 20, so 20, let us say this is 20. Now here to here no load, so no load. So now you have 30, so this goes to plus 10, so then it has plus 10, and then it came to 40 actually. And so 40 means here you have some minus 30. Okay, so some minus 30 it came out, and finally no load. So if you see, this continues like this. Okay, so this continues. This continues like this, right? So if you see, this is the shear force diagram basically here. So 40 increase, again 30 degrees, again 20 increase. Okay, so if you see these values, for example, this is 20, this is plus 10, actually plus 10 of course, minus and negative. So now if I ask you, for example, if I ask you, let us suppose if this length is 2 meters, this is also 2 meters, this is 1 meter, for example. Now if I ask you, let us suppose I am starting my x here, and my x is going like this. This is origin. Okay, this is origin. Let us suppose I have started here and my x is going like this. Now let us suppose if I ask you, what is the shear force value at x equal to 1 meter, for example. Okay, so at x is equal to 1 meter, what is the shear force value? If I ask you this question, actually speaking, if you see, at exactly x equal to 1, at this point it is 10, at this point it is minus 20. So you have two values to tell me. So which value you will tell me actually? So that's why if you see, there is some ambiguity here. For example, if I ask you what is the value of shear force at x equal to 0.99 meters, you will definitely say minus 20, because here comes the point. And similarly, if I ask you what is the shear force at x equal to 1.01 something like that, you will say definitely 10. But if I ask you exactly at x equal to 1 what is the shear force, then definitely there is some dilemma for you, because here it is plus 10 and here it is minus 20. So that's why if you see in some standard books and all, this line is not represented by a solid line, it is represented actually by some dotted line actually like this. Okay, because there is some discontinuity at the points of application. Okay, now anyhow, this is just one example which I'm quoting so that few people can relate, because I'm also from mechanical, I have some idea on that. But anyhow, let us try to understand what is a limit actually. Okay, so limit of a function, limit of a function, limit of a function. I'll define in the simple terms. Let me not make the things complicated. A value, or you can say, okay, it can be complex also sometimes. A value L is said to be limit of a function, f of x at x is equal to a if f of x tends to L as x tends to a. What is the meaning of this? Look, I'll tell you. For example, let us suppose you have some graph. This is y-axis and this is your x-axis. X, y, origin. Okay. Now, let us suppose there is some function like this. For example, okay, this is some function y is equal to f of x. Y is equal to f of x. Now, let us assume this point is x is equal to a, for example. Okay. So, let us suppose this is the point x is equal to a. X is equal to a. Now, try to understand one thing. Let us suppose this value is L. Okay, this value is L, and I'm telling you this L doesn't have any connection with this function. This L is just a number on y-axis. That's it. Okay, basically I'm telling you this L doesn't have any connection with this f of x or a. This L is just a value on y-axis. Now, initially, as I told you, as x is tending to a, so let us suppose x is initially in this neighborhood. Okay, so let us suppose x is initially in this neighborhood. Okay, when x is in this neighborhood, you can understand one thing. When x is in this neighborhood, you can get this. This is your f of x value. Correct? This is your f of x value. Now let us suppose as x is moving towards a, so from this point it came here, for example, because I'm telling you x is moving towards a. So this point gives you something like this, that this is your f of x value. Correct? Now let us suppose x still moved towards a, then definitely you can understand this is your f of x value. Correct? So here you can understand one thing. When x is moving towards this a, if this value is your f of x, you can understand this f of x value is moving towards your L. Correct? Now x tends to a. This means I told you x is in the neighborhood of a and x is moving towards a. Now whenever x is in the neighborhood of a, whenever this point is x is equal to a, x can be on the left side, means in the left neighborhood, or it can also be on the right side. So it can be on the right neighborhood also. So let us suppose if I take the right neighborhood, let us see what's happening. So let us suppose at this location, if this is the f of x value, then let us suppose if x is moving towards a, then what happens? This function will come something like this, s or no. So in this case also you can observe as x is moving towards a, this f of x value is moving towards L. So this means basically there exists some value L such that whenever we are moving your x close to a particular real number, immediately f of x gets adjusted to move to some number. Okay, so that's why we call this L as the limit. Okay, now fantastically I'll tell you one thing. Normally mathematically it is denoted as mathematically it is denoted as limit x tends to a, f of x is equal to L. Look, I am telling you again, f of x is never equal to L. Okay, but because of this symbol limit, we write this in this notation that limit x tends to a, f of x is equal to L. The meaning of this equation is as x is moving towards a, this f of x is moving towards L. This is the meaning of that. Okay, now there is concept of left hand limit and right hand limit, because whenever I'm telling x is moving towards a, I'm not mentioning the direction. So whatever direction you take, definitely f of x should move towards L. Understood? Even if I take that x is in the left side of a and moving towards right, or if I take x is in the right side of a and moving towards left, then in both the cases my f of x should move to L. That's the reason why if a limit to exist, left hand limit and right hand limit both should be same, because in the definition of limit they didn't specify the direction. Clear? So normally if you see, a minus is called left neighborhood, a minus is called left neighborhood basically, and this implies x belongs to a minus delta comma a. Similarly, a plus denotes a right neighborhood, right neighborhood, and this tells you that x belongs to a comma a plus delta, because if you see, if you take the total neighborhood a minus delta to a plus delta, a minus delta to a is the values of x, are the values of x which lies to the left side of a, correct, on a number line. Similarly, this belongs to the right side of the a, so that's why they're called left neighborhood and right neighborhood. One point I'd like to tell here, many students, even in previously in my offline classes and all, they used to commit this mistake. A minus is different from minus a. Okay, so look, whenever this is a number line, if this value is a, then minus a will be somewhere, you know, far away. Actually minus a will be somewhere here, because 0 is in between. There are many real numbers, but a minus are the values which are here. Okay, so a, this is a minus and this is minus a, somewhere far away. Okay, so that's called left neighborhood actually. Clear? So that's why you generally write this as, for limit to exist, for limit of a function f of x, for limit of a function f of x to exist, limit extends to a minus f of x. This should be same as limit extends to a plus f of x. Okay, the meaning of this equation is, if your x is on the left side of a and moving towards a, then this limit value should be same as if x is in the right side and moving towards x is equal to a. Okay, so that's the meaning of left hand limit and right hand limit, for example. Okay, now why you are substituting x is equal to a is because you take this equation, you know, for example, at this location, you know that this value, if the function is continuous, of course you can understand this L value is nothing but almost equal to this f of a value, correct? So whenever x is almost 0, it's almost touching a, this f of x is almost touching L. So whenever, actually in that calculation what I have shown you in this calculation, what you should actually do is, look, what you're actually doing is, you are not actually substituting 2. When x is tending to 2, you are substituting 1.9999 plus 2. So this is giving you 3.9999 and all, but this value is nothing but very close to 4. That's why you are actually substituting 2 and writing it as 4, because of this symbol here. Okay, if this symbol LT is not here, you are not supposed to substitute x is equal to 2. Okay, you actually need to substitute, whenever x is tending to 2, you should write only 1.999 or 2.00001 plus 2, and you should take 4. But since this limit definition is there, this LT is there on the top, that's why you are actually substituting 2. Okay, so I hope you understood this. So this is basically the meaning of limit. Whenever you are having any function, if as x is tending to a particular number on x-axis, if f of x is tending to one particular number on y-axis, then we say that limit exists for that function at that value of x. Okay, so this is the basic definition of limit. And before going further for continuity, all these things, I would like to give you some more popular, or you say most frequently used graphs actually. Okay, so let us see some graphs which are very important for you in the applications of differentiation and all. So some standard graphs, let me give you some standard graphs. Let me give you. So first of all, to draw any function, let us suppose if I give you some random function, if I talk about sin x, cos x and all, you know how to draw. But let us suppose if I give you some random function like x into sin x, sin x by x, such kind of graphs if I give you, what is the, how to basically proceed? Okay, what is the common procedure to draw any graph? Okay, so let us see here. That I'll explain you with one example. First, let us deal with the sinusoidal function y is equal to sin x. Okay, so when y is equal to sin x, so of course you all know that it's a wave shaped, but let me tell you in a step-by-step manner how actually we'll get the graph. Okay, so see here. First of all, first step is establish the coordinate system. Origin, you can say x-axis minus x-axis, y and minus y. Now, after establishing coordinate system, you should check for the maximum and minimum values of the function. If it has some maximum, okay, good. If it don't have also, it's good. You can draw the graph till infinity. Okay. So now if you see, we try to identify what are the maximum and minimum values of this function sin x. Okay, so we all know generally that sin x has the maximum value of y equal to 1 and minimum y is equal to -1, correct? So now let us see it. We know that it has maximum value that x is equal to 1. So let us draw the maximum value. We'll draw the maximum value that y is equal to 1. So this is some maximum value, and we'll also draw y is equal to -1 like this. Okay, so now if you see, this is y is equal to 1 and this is y is equal to -1. Now you know one thing, whatever you draw, you should draw in between these two lines, correct? Definitely there is nothing which is going to go above this line, and also there is no graph which is going to come below this line, because these are the maximum and minimum values. So definitely the graph should lie in between these two lines. So that's what you know. Now, so first point, establish the coordinate system, draw the coordinate system. Second point, identify the maxima and minimum values. Now third point, check if the function has any periodicity, means is it of any repeating in nature. Okay, so you should check for that. For example, you know, sin x is such function which is repeating after every 2 pi intervals. Okay, now there could be some other function which is repeating after pi intervals only. Okay, so we should check. The third point is to check for the repeating or periodicity of the function. Okay, so for example, sin x, you know, 2 pi is the interval, so let us split this into intervals of 2 pi. So let us suppose this is 2 pi interval, then this is one more 2 pi interval like this, basically. Similarly here 2 pi, one more 2 pi. Similarly here we can say lastly one more 2 pi like this. So you understood that there is some repeating in pattern. So in this part, let us suppose if this is x is equal to 2 pi, for example, x is equal to 2 pi, 4 pi. Similarly it goes like that. Okay, 0, so -2 pi, -4 pi like this. Okay, now what is the shape of the graph from 0 to 2 pi? You know, in 0 to 2 pi you focus, because once you know what is the shape in 0 to 2 pi, same loop will continue, correct? Same loop will also reflect to the left hand side. Now what is the shape of the graph from 0 to 2 pi? This is what you need to check. Okay, so once you check this, you know, at x is equal to pi, this value is 0. So let us suppose if this is x is equal to pi, for example. Okay, so you know, in this, if you draw the graph, you will get your graph like this. You know, it starts at 0, reaches maximum at pi by 2, then again comes to 0 at pi, then it goes to minimum at 3 pi by 2, and again it touches 0. So you know that this is the graph from 0 to 2 pi. So once you know, then just copy this, that's it. Okay, so if you copy this like this, similarly if you copy this again, you will get something like this, similarly, and many things like this. Okay, so this is how you generate the graph of sin x. Okay, of course I know that it's a very simple graph, you all can draw in a single go, but this is the general procedure for drawing any graph, complex functions also. Right now you know sin x, so that's why you'll draw very easily. But let us suppose if I ask you some complicated function, then you will be in trouble. Okay, so that's why these are the steps. First draw the coordinate system. Second, identify the maximum and minimum values. Third, check for any repetitiveness of the function, means is there any periodicity of the function, check for that. And fourth point, try to plot the graph in that one particular box so that you can just replicate it. Okay, now cos x. So cos x I'm not elaborating much, since you know, you might be very clear of this. So cos x, y is equal to cos x, y is equal to cos x. Again same graph here. X 0 minus x, y minus y. Then you have your maximum and minimum limits. So maximum is y is equal to 1, let us say, and y is equal to -1 is the minimum. So if this is y is equal to 1, and if this is y is equal to -1, then again you can identify certain periodicity for this also, 2 pi intervals. So 0 to 2 pi, then again 4 pi, minus 2 pi, minus 2 pi, and minus 4 pi, something like this. Okay, so this is minus 4 pi. Now if you draw the graph in between this, then definitely you know at cos 0 this is 1, and also if this is 2 pi for example, 4 pi, now you know cos 2 pi is also 1. So if you go for the graph, it goes something like this, correct? So similarly you can connect similarly here, similarly here. So if you draw the graph of cos x is something like this, such that the cos 0 value is 1, cos pi by 2 90, cos pi minus 1, cos 3 pi by 2 again 0, cos 2 pi again 1. So this basically goes on. Okay, so this is how you need to generate the graphs. Okay, so now, and as I told you in linear algebra class also, whenever you want to identify how a graph looks in general for your interest, Desmos is one very good graphing calculator. Okay, now third graph which I would like to give you is tan x. One very important limit I'll give you at this graph, y is equal to tan x, is, look, I'll tell you, tan x is also something like this, sin x by cos x. So you know, origin x minus x, y and minus y. Now you have done the coordinate system. Now you know if you ask for minimum and maximum values of tan x, you don't have any finite values, correct? In case of sin x and cos x, you have +1 and -1, but in case of tan x, you don't have any maximum or minimum values, so we don't have any limitations. Okay, leave. Now do tan x graph have any periodicity? Okay, this is what you need to check. Means is tan x graph repeating in nature? Yes, it is repeating, and the period is pi, means after every pi intervals the graph repeats. Okay, so let us check here. So if you check this, this is pi, then this is 2 pi, this is 2 pi, similarly this is minus pi, this is minus 2 pi. Okay, so this is minus 2 pi. Now if you see what is the shape of the graph from 0 to pi, 0 to pi, 0 to 2 pi. So again, to observe from 0 to pi, let us take 0 to pi by 2 also. Pi by 2 also let us take one value. So pi by 2, let us suppose you are splitting this at pi by 2, for example, for easiness, that's it. Okay, so if this is for pi by 2, then you know from 0 to pi by 2, the graph changes from 0 to, because tan 0 is 0, for it changes from 0 to infinity. Similarly from minus pi by 2 to pi by pi, it turns out like this. Okay, so this again continues. Similarly this again continues like this. Okay, so let me draw some neat sketch. So if you see, if you have some minus pi by 2 here, minus pi by 2, let us say, then the graph is something like this. It changes very steeply after pi by 4 actually. Similarly, if you have some one more interval here, so then you will have similarly, if you write one more interval like this, then the graph is something like this. Yeah, it starts here basically, and okay, so this is how the graph of y equal to tan x looks like actually. Okay, now here I would like to tell you one very important limit actually in this context. Look, if I ask you what is the value of limit x tends to pi by 2 tan x, x tends to pi by 2 tan x, so many of you directly say it's infinity, correct? Because you know if you substitute x equal to pi by 2, tan pi by 2 is infinity, but this limit actually does not exist. Okay, so this limit does not exist. Okay, this is the symbol for does not exist. Okay, normally these are called quantifiers, and this is doesn't exist. Now why this limit doesn't exist, I'll tell you. Look, Let us suppose if you calculate left hand limit, okay, if you calculate left hand limit, let me write completely. So if you calculate left hand limit, then limit extends to pi by 2 minus tan x. So if you see this value, now what is pi by 2 minus? This interval basically, okay. So this interval, this is pi by 2, so pi by 2 minus is slightly less. So we can understand one thing, as x is moving to pi by 2 in this direction, this f of x will move towards plus infinity, correct? So that's why this value is infinity. Now coming to right hand limit, if you take right hand limit, then in that case you can understand one thing, if I write limit extends to pi by 2 plus tan x, okay. So let us suppose I am writing extends to pi by 2 plus tan x. Now pi by 2 is here, so as x is tending to pi by 2 plus, that means x is somewhere here and it's moving towards this direction. So you can understand, as x is moving in this direction, this f of x curve is moving towards minus infinity, correct? So this value is minus infinity. So one value is plus infinity and another value is minus infinity, and you can see clearly these two are not same, and of course that's the reason why limit extends to pi by 2, tan x does not exist, okay. It's not like blindly you substitute x equal to pi by 2 and you feel infinity. No, that's the wrong way of answering. But actually if you see clearly visually, if you see x tends to pi by 2 plus and x tends to pi by 2 minus, if in one case it is minus infinity, in one case it is plus infinity and in another case it is minus infinity. So that's why this limit is one very important limit. Many times they ask you in exams with the first option as infinity, okay. So never fall in the trap of that substituting x equal to pi by 2 and writing infinity, okay. Limit extends to pi by 2 tan x does not exist, okay. So please keep this in mind. Clear? Now we have seen sin x, cos x, tan x. Then let us see some normal functions also. For y is equal to log x to the base a, let us suppose, okay. If I write log x to the base a actually, okay. Now because this is one very important graph that people ask you to draw in interviews actually, okay. Because even in my BARC interview also, there are few people with one of the person, there is one person for mathematics, and generally if you go for IIT interviews or sometimes PSU interviews also, like not HBCL and all, but research oriented, DRDO or ISR or maybe BRC, all these things, then definitely they'll be doing research, they'll be having very strong knowledge on mathematics, okay. So let us suppose if they ask you some mathematical questions, you should be able to answer them, okay. So this graph is one very famous graph that's asked in interviews, y equal to log x to the base a. Now as soon as they ask you this question, log x to the base a, if you straightly start drawing something, they understand that you don't know anything, okay. Why? Because this graph, the shape of this, shape is same, but depending upon the quadrants, actually the value of a depends, okay. Means basically if I give you, until and unless I give you the value of a, you cannot draw the graph, okay. Why? Because it has two different curves. Look, I'll tell you. First, if 0 less than a less than 1. Second, a greater than 1. So these are the two things. Now let us see how they look like. So let us suppose, so why am I writing? So this is a real variable calculus, so I am not considering negative axis for log, okay, y and minus y. So if this is the case, similarly here also let me draw. So let us suppose this is x, 0, y and minus y. Now in this case, if you see the graph of y equal to log x is something like this, okay. This is when 0 less than a less than 1. This is y is equal to log x to the base a, and coming to here, this is something like this, okay. So this is y is equal to log x to the base a, and of course when a is greater than 1. So normally this natural exponent, okay. So e, for example, e value is around 2.718, which is actually greater than 1. That's why log x to the base e, you will find the graph in this shape because a is less than 1, okay. Look, for example, I can show you because we'll use some Desmos plotting, so Desmos graphing calculator. So let us plot both on this graph. Okay, so first we'll plot something. I think yeah, here we have. So see here, log, we'll write to the log to the base, let us write base log, log to the base we can write as shift underscore yes log. So for example, let us write e for example. Okay, and then let us write x here for example. So log e to the base x, you can see log e to the base x. The graph is something like this. Okay, so basically this is your x-axis which I have shown, and this is the graph of y is equal to log x, like the shape what I have shown you. Of course this will be slightly steeper like this, but my intention is to just show you the graph. But let us suppose in case of e, if I have substituted some different value, say for example 0.3 something like that, 0.3 for example, then you can see immediately the shape of the graph got changed. It's now in the different turn. Okay, so that's why I have given you two different graphs. Whenever a value changes, basically the shape of the graph changes. Okay, so in interviews, if someone asks you what is the shape of that function, means if they ask you to draw, immediately the first question you should ask them is, sir, what is the value of a? Okay, then let us suppose if they tell a is equal to 1, because I have given you for 0 less than a less than 1 and also a greater than 1, but exactly at a equal to 1 you don't have any logarithms. Okay, log to the base 1 does not exist because that's not unique actually. Okay, so that's the reason. So anyhow, if you see, this is 4 and this function is continuous. Anyhow, we'll see what is continuous and all. Now fifth, y is equal to e power x. E power x, if you take, then definitely e power x graph is something like this. So exponential functions are not negative, means basically at least when the base e. So if you draw the graph of y is equal to e power x, it goes like this. Okay, so this is y is equal to e power x, and at x is equal to 0, this value is 1. Okay, so this value is 1 and this is 0. Okay, so x, y and minus y. Okay, so this is y is equal to e power x. Why I am drawing all these curves? Because we after some time will will deal with something called multiple integrals, or you deal with area under the curves, all these things. So that's the reason why I am giving you this. Okay, you will find length of the curves. Okay, so all these things we'll discuss in detail. Okay, so sixth, y is equal to e power minus x. This is very simple now. Okay, because you see, whatever are the values of y that are coming for positive values of x, same values will come here but for negative values of x. Okay, means this gets reversed actually. Okay, so if you draw the graph, it looks something like this. Let us move here. 0, x minus x, y minus y. Okay, now if you see, the graph is something like this. If you draw, it comes out to be something like this. Okay, so this is y is equal to e power minus x, and again of course when you put x is equal to 0, this value is going to be 1 at this location of x is equal to 0. So this is the graph of y equal to e power x and y equal to e to the power minus x. Next, I'd like to give you graph of some mod function. Y is equal to modulus of x. Okay, so y is equal to modulus of x. So it's very easy. So origin x minus x, y minus y. Okay, now basically this function y is equal to mod x is actually defined like this also. X when x is greater than 0, minus x when x is less than 0. Okay, you can put equal to at any place, maybe on the first part or second part. So the meaning of this is, whenever mod x function is always positive, means if I take even modulus of negative values, I'll get the absolute value. Means basically if I hit mod of minus 4 or minus 5 something, again I'll get 5 or 4. That's the reason. Okay, so y is equal to mod x. Now you can understand one thing: if x is negative, then minus x is positive, and if x is positive, directly it is x. Now whenever x is greater than 0, means let us suppose x is greater than 0 is to the right side of this y-axis. Okay, so that's of the form y is equal to x actually. Okay, so when x is greater than 0, when x is greater than 0, the equation is y is equal to x, or maybe you can put a equal to sign also. When x is less than 0, this y is equal to minus x. Okay, so first y is equal to x line, how does it goes on? It goes something like this. Okay, so this is y is equal to x, y is equal to x. When x is less than 0, this becomes y is equal to minus x. Okay, so something like this. Okay, so y is equal to minus x, y is equal to minus x. That's the reason you have. Okay, now try to understand one thing before. Okay, I'll define what is continuity and all, how to check this mathematically and all, but right now I'll ask you one thing: from minus infinity to infinity, is there any breaking of this function? Did this function broke anywhere? No, it's a continuous graph. Okay, you can see there is a continuous function, there is no any discontinuity, means there is no breaking of this function anywhere. So that's why mod x is continuous, mod x is continuous for all real numbers. Okay, there is nothing like mod x is not continuous. Mod x is continuous for all the real numbers. Okay, so anyhow, this is the mod x function. Next, I have given you 7 graphs. Okay, fine. So next, 8th graph, I would like to give you 8th one. So we have talked about trigonometric functions, exponential, logarithmic, algebraic functions. Let us talk about. Okay, so y square is equal to 4ax, for example. Y square is equal to 4x. So from this you can understand one thing: whatever the value of y, x is always positive. Correct? Means this function is not defined for negative values of y. Negative values of x actually. Okay, so if you see, negative values of x are not defined, so this is 0. Your graph looks something like this. Okay, symmetric, of course, symmetric. Okay, so symmetric. So this is y square is equal to 4x. Y square is equal to 4x. Similarly, if you write x square is equal to 4ay, 9. X square is equal to 4ay. Okay, so if you see, now we can again plot that, you can again identify that y is never going to be negative. So that's why if you see the graph like this, if this is origin, x minus x, y minus y, then the graph looks something like this. Okay, so this is x square is equal to 4ay basically. Okay, so this is how we have different graphs. Okay, so now let me, before concluding this, okay, I have given you some 8 to 9 graphs which are useful. Now before concluding, I would like to give you 2 important graphs actually: x into sin x and x sin x by x actually. Okay, why sin x by x I'm giving, you will come to know when I teach you the concepts of maxima and minima. Okay, anyhow, let us see for now. So first, I hope it's 10th one, right? Yes, 10th. So y is equal to x into sin x, x into sin x. Now it's till now almost all the graphs what I have done, right? Now how to draw this graph? Okay, so first set up the coordinate system as usual. Set up the coordinate system. Set up the coordinate system. Origin x minus x, y minus y, y minus y. Okay, now x into sin x. So minus 1 less than or equal to sin x less than or equal to 1. Correct? So if you multiply x on all the sides of this inequality, minus x less than or equal to x into sin x less than or equal to x. So which means one thing is very clear: this x into sin x function lies in between the lines y equal to minus x and y is equal to x. So let us draw them. First of all, y is equal to x. If you draw y is equal to x, the y is equal to x function looks something like this. Correct? This is y is equal to x. Y is equal to x. Similarly, if you draw y is equal to minus x, so this is y is equal to minus x. Y is equal to minus x. So you can see the magnitude of this function is controlled by these two functions, but the shape of this function is actually controlled by this sin x. Okay, means basically if you see at x is equal to 0, this function is 0, but after that also the graph is having same shape like sin x because of this function in multiplication, but the magnitude means basically amplitude of this function will keep on increasing. This is x. So if you see the function means, you know, at x is equal to pi, at x is equal to pi, okay, at x is equal to pi, for example pi is somewhere here, at x is equal to 2 pi, then at x is equal to 3 pi, at all these places this function is again going to be 0, correct? So similarly at x is equal to minus pi, x is equal to minus 2 pi, like this. So if you see, now you just need to plot the graph in between. Okay, so it starts at 0, again at x is equal to pi, it touches here. So if you see the graph comes out, you know, it can't exceed, but it will be almost the same. Okay, so this graph will be almost similar to x square graph here. So if you see, it comes like this, then again it goes, it comes like this, then again it falls like this, and obviously that amplitude keep on increasing. Similarly here also, if you see, let me, so like this. Okay, so it increases, basically it is symmetric about, this is pi which I have written, let me draw it different ink. So this is pi, actually this is 2 pi, this is 3 pi, and so on. Okay, similarly here this is minus pi, minus 2 pi, and so on. So if you see, this amplitude keeps on increasing. Okay, so if you see, like for example underdamped systems and all, in that cases what happens, the amplitude of the vibration keep on increasing. Okay, even in signals and systems, when noise becomes very high, the amplitude of the noise keeps on increasing. So that's how we'll take this function y equal to x into sin x, one very important function in general, and of course it don't have any maximum value, because if you see, as you go on, the amplitude of the function keeps on increasing. Okay, so that's why y is equal to x into sin x looks like this. Okay, here I would like to give you one very important point or thumb point actually, that look, I'll tell you, if y is equal to, means basically, you know, if f of x is equal to minus if f of x is equal to, or if f of minus x, let us say, is equal to f of x, if f of minus x is equal to f of x, then f of x is called even function, then f of x is called even function, then f of x is called even function. Now what is the meaning of this even function? Look, if you write the series expansion, which we will see later in Taylor series after some 1 hour time, so if you see why this is called even function, actually if you write the expansion of this x into sin x, every term will have a even degree. Okay, why? I'll tell you. Look, for example, I'm telling you x into sin x is something like this. Actually x into sin x is equal to x times of x minus x cubed by 3 factorial. Why this expression is coming, I'll tell you in Taylor series. Okay, so right now sin x expansion is this, x power 5 by 5 factorial minus x power 7 by 7 factorial plus, and so on, this goes on till infinity. Okay, so if you see, when you multiply x with all these terms will have some even powers. Okay, so plus x power 6 by 5 factorial plus, and so, or minus, you can say minus x power 8 by 7 factorial, and so on, this goes on actually. Okay, so if you see, every term have a even power. Okay, so that's the only reason it's called a even function. And you will observe one thing, if this means if you plot these even functions on xy coordinate system, like for example this function is also a even function. Okay, because if I calculate f of minus x, this gives me minus x into sine of minus x, and you know, my sine of minus x is nothing but minus sine x, so minus x into minus sine x, so minus into minus gets plus again, so this is again x into sine x. So if you see, this is same as your f of x. Okay, so that's why this function is even function, and whenever you plot any even function, these even functions are symmetric about y-axis. Okay, so I'm repeating, whenever you plot about whenever you take even functions, the graphs of the even functions will be symmetric about y-axis. Okay, so let me show you the actual graph, how it looks like. So anyhow, we have the Desmos here. So see here, x into sin x, x into, where is this into, yeah, here, x into sin x. Okay, so if you see, the graph is something like this. So the graph is something like this, okay, which we have tried to draw now. So if you see, from 0 they increases, again they fall, and again they go up. Okay, so from 0 they increases, and again they fall, and again they increases. Okay, so this is the graph basically, and if you try to shrink this, this is how you can see clearly it's increasing. Okay, so and if you connect all these points, it is 0 comma 0, this is almost y is equal to it is controlled by sin x. Okay, so all these points, they have x and y coordinates equal. Okay, all the poles have x and y coordinates almost same. I think this is rounded off to something, but normally if you see, they are controlled by this line y equal to x and y is equal to minus x actually. Okay, and this graph is symmetric about y-axis because it is an even function. Clear? I hope it's clear to you. Okay, now let us go for one last graph, which is again some important graph. Y is equal to sin x by x. Y equal to sin x by x. Okay, so y is equal to sin x by x. If you plot this, this is again one very important graph. If you plot this, look, the graph comes out like this. This is also even function. So this is your x-axis, then this is going to be your y-axis. So 0, okay, 0, x, y, minus x, minus y. Now try to understand something. Again, minus 1 less than or equal to sin x less than or equal to 1. So if you divide with 0, if you divide with x, minus 1 by x less than or equal to sin x by x less than or equal to 1 by x. Okay, so first of all, one thing, this sin x by x lies in between 1 by x and minus 1 by x. So how does the graphs of y equal to 1 by x and y equal to minus 1 by x look like? Look, y is equal to 1 by x will take this form, rectangular hyperbolas. Y is equal to 1 by x will take this shape. Okay, of course you won't deal with negatives, but many of you in thermodynamics or something in your +1 level at least, or in mechanical it's quite often. So if you plot a PV diagram for isothermal process, okay, so in isothermal process you all know this, PV equal to MRT. PV is equal to MRT. So of course, for a closed system executing isothermal process, if you see, this term is a constant. So PV is equal to some constant. So you'll get pressure is equal to some constant by volume. So there you will draw rectangular hyperbolas actually, because that is again same as this function y is equal to some 1 by, of course, if I take this y and if this is x, y is equal to some constant by x. Okay, this constant value we are taking 1 in this case. That's it. Okay, now similarly y equal to minus 1 by x, how does it look like? Y equal to minus 1 by x. Y equal to minus 1 by x look like this. Y is equal to minus 1 by x. Okay, now if you draw the graph, again, is there any periodicity? Yes, there is periodicity, because at x equal to pi, 2 pi, 3 pi, all these values, this sin x becomes 0. So 0 by 2 pi 0, 0 by 3 pi 0. Okay, so that's how at all the pi multiples this sin x becomes 0. So if you take some values here, pi, you can say, for example, then 2 pi, then 3 pi. Similarly, if you have minus pi, if you have minus pi, minus 2 pi, then minus 3 pi. If you have like this, minus 3 pi. So see here, 0, 0, pi, 2 pi, of course 3 pi and all. Similarly, minus pi, you can write minus pi, minus 2 pi, minus 2 pi, minus 3 pi and all. Why I'm spending so much time on these graphs is because they are very much important for you in coming topics. Okay, whenever they are talking about area between the curves or double integrals especially, or multiple integrals, you can say, when you are talking about multiple integrals, plotting these graphs is really important for you. Okay, so that's why I'm giving you all this. And also in vector calculus, of course, in vector calculus also, when you are talking about Gain's theorem and all, you will talk about multiple integrals, and those multiple integrals are very much important. And actually knowing these graphs is very much important for you to draw the multiple integrals then. Okay, so see here. So now I would like to tell one point here. Let us suppose exactly at x is equal to 0, exactly at x is equal to 0, is this division possible? Means basically, is this function having any value? You will, if you put exactly x equal to 0, sin 0 by 0, 0 by 0, division is not defined, so that's why exactly at x equal to 0 you don't have any value here. Okay, but apart from x tends to apart from x is equal to 0, the function has a very great shape like this. For example, you can say it should pass 0 like this. Okay, similarly, if you see, all this, it passes. Okay, now if you see, intentionally I did not touch this function to y-axis. Okay, because exactly at x is equal to 0, this function has not defined. Okay, but what is this value? Means to which value this function is going actually. Okay, so this value which I'm highlighting here is actually 1 on y-axis, because you all know one limit x tends to 0 sin x by x, which is 1. How this is 1, I'll again tell you with the help of Taylor series, but right now you believe me. So limit x tends to 0 sin x by x is equal to 1 actually. So that's why you can understand one thing: whenever x is coming very close to 0, this function sin x by x comes very close to 1 on y-axis. Okay, so that's how I know that this is 1. Here at this point, I would like to tell you one very important point. What is the maximum value of sin x by x? Okay, so maximum value of sin x by x is 1. Okay, because you can see clearly from the graph that as you go, this graph keep on increasing and this function value keep on increasing. So this is 1, and at the same time minimum value, if you talk, here comes the minimum value. So this minimum value is basically at x is equal to 3 pi by 2. Okay, so at x is equal to 3 pi by 2, this function has the minimum value of y. Okay, and actually if you see, this is sin 3 pi by 2 by 3 pi by 2 you can write, or here you can write basically here, if x is not positive, if they give you x is negative or positive, then this is the value. But if they give you x is only positive, then this is the value. Only sign changes. Okay, because if you see here, this gives you some positive value, basically sin 3 pi by 2 divided by 3 pi by 2, that gives you some positive sense actually. But right now if you see, for the whole plane, this is the minimum value. Okay, but anyhow, keeping in touch, this maximum value, identifying this maximum value is one very good very important thing for sin x by x function. Clear? So this is basically we finish all the graphs actually. So these graphs are very much important for you to understand in the real area under the curves. So some applications, basically if you talk about applications of differential calculus, then these curves are very important. Clear? So till here we'll take part 1, we'll join the other video. Okay, so let us continue. So basically we have seen these graphs, some standardized graphs actually in calculus, which could help you at the later topics. Okay, so now let us talk about one very important thing, which is continuity of a function at a point. Continuity of a function, continuity of a function, continuity of a function at a point, at a point. So what is continuity of a function at a point? So basically, from the meaning of continuity, you mean to say that the function don't have any break actually at any point. Okay, means let us suppose if you take a function, for example, say something like this. If this is your x-axis and if this is your y-axis, for example, let us say, then if this is your origin x, y, which is basically some function of x, So if you see, if I draw a function, this function has to be continuous like this. Okay, there should not be any breaking in between. Then we say that the function is continuous, and of course limit, continuity, all these are talked at a particular point. So if you take for example x is equal to a, something like this, x is equal to a, then let x is equal to a, if the function has to be continuous, the function should not break at x is equal to a basically. Okay, so mathematically how do we check whether the function is actually continuous or not? Okay, so for checking mathematically, first of all let me explain you one thing. Look, let us suppose the function is discontinuous here, for example. Okay, let us suppose the function is discontinuous here, and many times you might have seen functions like this: f of x is equal to 1 by x minus 2 when x is not equal to 2. Then at x is equal to 2, since this function is not existing because division with 0 is not defined, so they will define some values, for example say pi by 4, something like this. Okay, they will define some value. So these kind of functions you have seen, and these functions are called split functions. Okay, means because at x equal to 2 there is some discontinuity for this function. This function is not defined basically because division with 0 is not defined. They give you some other value of y. Okay, so these functions are called split functions. Okay, so now let us suppose this is defined somewhere here. So f of a is defined somewhere here, for example. Okay, this is your f of a. At x is equal to a, f of a is defined somewhere here, and at other parts the function is continuous. Now I want to tell you one very important thing here. For the function, even if the function is discontinuous, still limit can exist. How? Look here, I will tell you. Let us suppose if this value is L, for example. Okay, if this value is L, then you can understand one thing. Let us suppose if x is here, if x is here means in the left neighborhood, so then if you see, this is your f of x value, correct? This is your f of x value here. This value is your f of x. Now let us suppose if x is moving towards a, let us suppose from this point it moved somewhere here. So as it's moving towards x is towards a, your f of x is moving towards L. Okay, so similarly if you take one more point here, somewhere here, if you take, yes, so somewhere here slightly if you take, then you will again observe this f of x is basically moving towards L. Similarly in the right side case also, if x is initially at this location, then if you see your f of x value is somewhere here, then when x is moving towards a, let us suppose it got slightly moved here, then your f of x value is again tending towards L. So basically you can see one thing, this function is not continuous at x is equal to a. There is clearly, you can see there is a breaking at that point, but still as x tends to a, means if this point is a, as x is moving to a from both sides, this f of x values are moving towards L. Okay, so you can observe one thing, even though the function is discontinuous, limit of the function still can exist. Okay, so that's how. So basically now I am talking about this function being discontinuous because there is a breaking here. Now how do we check mathematically at a particular point whether this function is continuous or not? Okay, how do we check that? Look, a function y is equal to f of x is said to be continuous, at x is equal to a if limit extends to a, f of x is basically is equal to f of a. What is the meaning of this? Look, how did this equation come? See here, I'll tell you. Look, let us suppose if this point comes here, for example. Okay, this point we have slowly dragged and kept it here. So this point is now acting as a bridge for these two parts, and it is connecting the curve. Okay, now whenever this point comes and sits in this gap, then definitely this function becomes continuous, correct? What is the mathematical meaning of this point physically coming here? This f of a coming to L, correct? So if this f of a is coming equal to L, that means this point is actually coming and sitting here and making the function continuous, correct? So means basically this f of a should be equal to L, and L is nothing but limit extends to a f of x. So that's how if a function has to be continuous, its limit at that particular point should be equal to the functional value. Okay, look, as I told you, even if the function is discontinuous, still limit can exist, but if the function has to be continuous, definitely this limit has to be equal to the functional value. Clear? So we'll write a note here. Note, if limit extends to a, f of x exists, then the function need not be continuous at x is equal to a. Need not be continuous at x is equal to a. Okay, so at x is equal to a, because you have clearly seen at this point previously the function was discontinuous, but still the limit got existing. Okay, so that's how, if function has to be continuous, limit should be equal to the functional value. Okay, if these two are not equal, even though this exists independently, but still the function cannot be continuous. Okay, so that's how this property is actually very important. Okay, if limit exists, function need not be continuous, but if function is continuous, then definitely limit is existing. Okay, because if we want to show this equality, definitely should have some value here, so this limit should definitely exist. Okay, so that's how we'll talk about continuity. Then we move on to one very drastic application, I would say, differentiation or differentiability of a function. Differentiability of a function. Differentiability of a function. Now see here, what is this differentiability of a function? Means basically when you say a function is differentiable at any point, for example. Okay, so we'll write it this way: a function y is equal to f of x is differentiable at the point at the point x is equal to a, is differentiable at the point x is equal to a if limit extends to a, f of x minus f of a divided by x minus a. This limit exists. Now what is this limit basically, and how do you write this? Okay, this is written as, it is denoted as f dash of a, which means basically f dash of x at x is equal to a. This is equal to limit extends to a, f of x minus f of a divided by x minus a actually here. Okay, so this is how we denote this. And who gave this formula? Basically, why f of x minus f of a? You know, derivative is nothing but dy by dx, correct? What dy by dx tells you? Actually, look, if you add dy by dx, that value talks about when you change a small quantity in x, which is dx, what is the change in y? That's what dy by dx talks about. Okay, so look here, let me explain you graphically also. Let us suppose this is some x-axis and y-axis, for example. Then you have origin x, y, like this. Now let us suppose you have some function basically. Okay, so you have some function like this. Now if this is y is equal to f of x, now let us understand one thing. Let us suppose this point is x, or a, x is equal to a, for example. Okay, this is a, x is equal to a, and this point which is here slightly, okay, actually the points x and a are very close, but since to make things clear, I am putting them apart. So this is x. Now tell me one thing, if this is x is equal to a, then definitely this value is nothing but f of a, correct? And similarly this value is f of x. Now if I want to calculate delta y by delta x, means let us suppose if I am interested in finding, if I give a small change to x at this location, means initially my x is at a. Now let us suppose if I am changing this x by a small amount, if initially x is here at this point a, so slightly I have given change. So when I slightly change the value of x, what is the corresponding change in y? Okay, that's what I am interested at. Okay, so look, what is the change in x I am giving? X minus a. This is the change I am giving, correct? Because this x minus a is the difference, so this is the change in x. So this change in x is bringing a change of f of x minus f of a. F of x minus f of a is the change in y. But since limit, continuity, differentiability, all these are defined at a particular point, so if this length has to be some point actually of very small length actually, then this x minus a distance or this length has to be very small, which means almost 0. If x minus a tends to 0, means if x minus a is going to be very small, that means x is going to be very close to a. So that's what we write. Limit, this implies dy by dx at this location. Of course, we are talking at the point x is equal to a, is nothing but limit x tends to a, f of x minus f of a divided by x minus a. Okay, so and of course this is denoted as f dash of a, which we have written here, f dash of a. So this is how we have got the result. Okay, so now basically this is the condition to check whether at a particular point limit exists or not. Okay, so if this limit is existing, then definitely the function is differentiable, and the value of the differentiation is the value of this limit. Okay, if this limit does not exist, then the function is not differentiable. Okay, so this is the simple way to identify what is a derivative. Okay, but before this there is again one principle which is called the first principle of differentiation. Okay, so what is the first principle of differentiation? Look, same thing. Let us suppose this is your x-axis and this is your y-axis, for example. So this is your origin x, y. So this is y is equal to f of x again. So y is equal to f of x. Okay, so if y is equal to f of x, then this is the value of x, let us say. Then obviously let us suppose this corresponding value is x plus h. H is some some constant such that we have given some small increase to x. So this is x plus h. So correspondingly what happens, this value will be f of x, and this value corresponding here will be f of x plus h. Okay, so this value is f of x plus h. So now if you calculate delta y by delta x, delta y by delta x is actually equal to, now we did not take any particular point a or something, we have taken some random value on x-axis. Okay, so delta x is basically x plus h minus x, and f of this is f of x plus h minus f of x. Okay, so this is delta y by delta x. So if you want to calculate at any particular value of x, this length has to be a point actually. So that means this x plus h minus x, this difference should tend to 0, which means if you simplify, h tends to 0. So that's why if you see, if you want to write this expression in terms of small differences dy by dx, this is actually delta y by delta x is some big change. Okay, so if that has to be a point instantaneous, we'll write dy by dx. So this is limit h tends to 0, f of x plus h minus f of x divided by h actually, because x gets cancelled. So this is h, and this formula you have seen at many locations. Okay, and this is called the first principle of differentiation. Okay, so this is called first principle of differentiation. Okay, so this is called first principle of differentiation. Now using this first principle of differentiation, you can calculate limit of any function. Okay, of course the function should be continuous. So if you see, because when I am talking about x plus h tends to x, this point should come to this point very smoothly. Okay, there should not be any breakings here in between, because this x plus h is coming towards x, then definitely this point should come to this point smoothly. So there should not be any breaking of the function in between. So that's why if you see, this is the way how you get it actually. Okay, so this function is actually this is basically denoted as f dash of x also. So this is also called f dash of x. So if I give you some function, some continuous function f of x, then you will calculate this limit, and if this limit exists, you will say the function is differentiable. Okay, this is in general at any location. This is in particular at a location x is equal to a. Okay, both are identical. You can see in the expressions we have observed that. And here I would like to add one point. Look, for example, let us suppose I have given you some function f of x is sin x. Now if I ask you what is f dash of, for example, say pi by 360, for example. Okay, let us suppose if I ask you what is this value, f dash of pi by 3 basically. Okay, now you will calculate, how you will calculate? First of all, you will calculate f dash of x. F dash of x is equal to, if f of x is sin x, derivative of that is cos x. then you will substitute this value f dash of pi by 3 is equal to minus is not there, so cos pi by 3. So cos 60 is basically 1 by 2. So what is the meaning of this 1 by 2? Okay, obviously if I give you any function and if I give you some point, you will get some number. You will differentiate the function, substitute x is equal to something, then you will get some number. But what is this number telling you actually? Okay, so this number is actually telling you this value. Look, let us suppose if this is your x-axis, if this is your y-axis, so origin x, y. Now if you take the function sin x, let me draw. So this is the line y is equal to 1, for example, say like this. This is the line y is equal to 1. So sin x graph, if you plot the sin x graph, it comes out like this. So it starts from 0 and goes to pi by 2 like this. So and afterwards it again falls to pi, but of course I'm taking only till pi by 2. Okay, so I'm taking only till this pi by 2. So if this is pi by 2, then what this 1 by 2 is telling you, if you take this point x is equal to pi by 6 somewhere here, for example, if you take this point x is equal to pi by 6, okay, pi by 3 I have taken. Okay, so x is equal to pi by 3. For example, if this point is pi by 3, x is equal to pi by 3, then this is the point on the curve. So what this function tell you is, if you draw a tangent to this function at this point, x is equal to pi by 3. Okay, so let us suppose I am taking some tangent to this function at x is equal to pi by 3. Okay, so at x is equal to pi by 3, if I take a tangent, then this tangent will make some angle with the x-axis, correct? So this angle is theta. So tan theta value is equal to 1 by 2. This is what we mean. Okay, so geometrically this value 1 by 2 tells you that at x is equal to pi by 3, if you draw a tangent to this curve, then the angle made by the tangent to this x-axis is theta, then tan theta value is equal to 1 by 2. Now it's very clear, if we change the point, this value changes. Similarly, let us suppose instead of pi by 3, if I draw some tangent here, that tangent will make some different theta, but the theta will be in such a way that tan theta value will be equal to f dash of that function at that particular point. Okay, so f dash of a practically means the slope of tangent to the curve at the point x is equal to a, and you know slope is nothing but tan theta for a straight line. We have seen basically. Okay, so if 2 points are connected, x1 y1 and x2 y2, if these are the 2 points which are connected by a line segment, then slope is given by tan theta, which is y2 minus y1 by x2 minus x1. Okay, and if you clearly observe, this is nothing but difference in y divided by difference in x actually. Okay, change in x and this is change in y. So all these are basically it's very in sync to each other. And also you have done this form, correct? If I ask you this equation ax plus by plus c is equal to 0, which is a linear equation, of course. If I ask you what is the slope of this line, basically it's a straight line. So if I ask you what is the slope of this line, many times you feel some ambiguity, like if it's minus a by b or minus b by a, there is always some confusion in your mind, but you can simply tell this. So as I told you, slope is nothing but derivative. Let us differentiate this function with respect to x. Why we are differentiating with respect to x? Because y is the dependent and x is independent. Theta is with respect to x-axis, so that's why we need to differentiate with respect to x-axis x. Okay, so if you differentiate this function with respect to x, a into derivative of x with respect to x is 1 plus b into dy by dx. Differentiation of a constant is 0, so is equal to 0. So dy by dx is equal to minus a by b, minus a by b. So this is the slope of this linear equation. Okay, and also if you can convert this, and of course without the differentiation also you can tell how you can convert this equation into y equal to mx plus c form. Okay, so then this m is the slope. If you convert, let us see what happened. Y is equal to minus ax minus c by b by b. So y can be written as minus a by b into x plus minus c by b. Okay, so you can see this is the slope minus a by b, which is the same value as compared to this. Okay, so slope is basically tangent of the slope of the differentiation is nothing but slope of the tangent to that function at that particular point. This is very important. Okay, because we'll use this point many times in the upcoming concepts in this calculus video. Okay, so this is how we got the slope. Okay, now Anyhow, so straight away let me give you some very important formulas of differentiation, then we'll go for limits once again. Okay, because why you need differentiation formulas for solving limits is, in limits we have something called L'Hospital's rule. Okay, so we actually need some differentiations of the functions when applying L'Hospital, so that's why we'll go for some standard differentiations in the beginning. Okay, so some standard derivatives which many of you generally might know. So some standard derivatives, some standard derivatives, some standard derivatives. Let us see what are this. First, let us start with algebraic function. D by dx of x power n is equal to n times of x to the power n minus 1. Okay, so you can substitute whatever the value of n is there and you can just write the differentiation. Next, d by dx of sin x, d by dx of sin x, which is cos x, then d by dx of cos x, which is minus sin x, derivative of tan x, secant square x, derivative of cot x, minus cosecant square x, minus cosecant square x, then 6 d by dx of secant x, you can say secant x, which is secant x into tan x, then d by dx of cosecant x, cosecant x, this is minus cosecant x into cot x. Okay, so this is what you have, 8. So basically these 6 trigonometric functions got finished. Let us go to inverse trigonometry. D by dx of sin inverse x is 1 by root of 1 minus x square, and of course mod x is less than 1 in this case, because if obviously sin cannot take any value between any values out of plus and minus 1, so that's why mod x is less than 1. Similarly here, d by dx of cos inverse x, this is minus 1 by root of 1 minus x square. Similarly here also mod x is less than 1. Now similarly 10 d by dx of tan inverse x, d by dx of tan inverse x, this is 1 by 1 plus x square, and how many formulas I have given you? Some 10 formulas. Okay, 11. D by dx of cot inverse x, d by dx of cot inverse x is minus 1 by 1 plus x square. 12. D by dx of secant inverse x is 1 by mod x into root of x square minus 1, and of course in this case mod x is greater than 1, because cos always lies between plus and minus 1, so definitely secant will go out of plus and minus 1 always. So 13th, d by dx of cosecant inverse x. Sometimes generally secant inverse and cosecant inverse are very rarely asked, but still it's good to have them. X square minus 1 mod x greater than 1. Okay, so now coming to some exponential functions, d by dx of x power x, if you take, this is x power x into 1 plus log x to the base e. Okay, so 1 plus log x to the base e. 15th, d by dx of a power x, for example. So this is a is some constant, so a power x into log a to the base e is what you have. Then 16th, d by dx of log x, log function generally, so log x to the base a, if you take 1 by x times log a to the base e is what you have. Okay, so 17th, so definitely if you keep e power x here, you will get e power x into log e to the base e, log e to the base e, log of anything to the same base. If these two are equal, then log value is 1. So that's how differentiation of e power x is e power x, and differentiation of log x to the base e, natural logarithm, if you take, this is 1 by x, because this log a to the base e value turns out to be 1 in that case. Okay, so generally these are some normal formulas that you will be in need of for this differentiations, derivatives in general in this course. Okay, so that's why I have given you. So similarly, if you say hyperbolic functions, d by dx of sine hyperbolic x. Okay, So this sin hx is nothing but cos hx. Okay, so what are these hyperbolic functions? Basically I'm just giving you the formulations, but practically they have very big significance. E power x minus e power minus x by 2, and cos hx is e power x plus e power minus x by 2. Okay, so that's how you have the hyperbolic functions defined actually. Okay, now I'd like to give you two one important tool, which is product tool of differentiation, which is again known to you, product tool of differentiation, or sometimes you call this as UV rule. Okay, so product tool of differentiation, product tool of differentiation, product tool of differentiation. So basically if you have two functions, for example, okay, so let us write d by dx of f of x into g of x. So this is first function into differentiation of second function, d by dx of g of x plus differentiation of first function, d by dx of f of x into second function. Okay, so this is how you have, and you have the division rule also, a quotient rule. So let us write that as well. So because these are just fundamentals, majority of this chapter you might have found in your +1 +2 levels, but of course we'll also teach some advanced things. But once you know some good, if you know this chapter in a good way, then definitely this will help you further chapters like differential equations, vector calculus, complex calculus, all these chapters. Okay, so anyhow, let us see quotient tool of differentiation. Quotient tool of differentiation. So quotient tool of differentiation, quotient tool of differentiation. So if you take the ratio of two functions, d by dx of f of x by g of x, if you take out, then this is g of x into f dash of x minus f of x into g dash of x divided with this, divided with g of x whole square. Okay, because we'll be using these expressions after some time, so that's why I'm giving you this. Okay, so quotient tool of differentiation is basically this value. Now so we have got idea on some differentiations, so let us try to see some limits. Okay, because we have just seen the definition of limit, but there are some important points where we'll use these derivatives in limits. Okay, but before that I would like to give you one function which is actually very important. I forgot. So let us see here, greatest integer function, greatest integer function, greatest integer function, or sometimes it's also called step function, step function. So how this function is defined, let us see. Or step function. So how this function is defined, f of x is equal to n for all x n less than or equal to x less than n plus 1. Please make a note here, I'm not putting the equality sign. Okay, if you want I'll highlight this equality with a different color as well. So this equality sign is not here. Okay, so where n is some integer, where n belongs to z, n is some integer actually. Okay, n is some integer. So this is how the greatest integer function is defined. Means if you take, for example, it is denoted by this symbol, it is denoted by this symbol, square brackets on x. Okay, so integer part x is basically defined by this integer part, means basically this x with the square brackets on both the sides. Okay, now how we actually see this, for example, if I take 1.542, for example, this 1.542 is in between two integers. What are they? 1 and 2, correct? So 1 less than 1.542 less than 2. So this is n, this is n plus 1. So definitely this value is equal to this n value which is here, which is 1. Similarly, if you take minus 1.297 something like this, then you can see this value is nothing but minus 2 less than or equal to, or minus 2 less than minus 1.297 less than minus 1. Okay, because you see in negative numbers, as you go towards the left side, the values decreases. So minus 2 is less than this, so this is the integer part x function. So this is minus 2. So you need to write this. So basically whenever you take a real number, the integer which is left of that real number is the actual answer. Okay, and if the number itself is an integer, then that itself is the integer part value. Okay, so if you draw the graph of this function, look how it comes out. I'll tell you. So this is your x-axis, for example, and this is your y-axis. Let us say this is your y-axis, this is your y-axis. So 0, x minus x, y minus y. Okay, so now if you check this, let us divide this at x is equal to 1, x is equal to 2, all these values. Okay, so this is x is equal to 1, this is x is equal to 2, this is x is equal to 2, this is x is equal to 3, x is equal to 3, and you have x is equal to 4, something like this. So x is equal to minus 1 is like this, then x is equal to minus 2 is like this. So let us write the values 1, 2, 3, 4, minus 1, minus 2, like this. Okay, now let us also write y is equal to 1. Y is equal to 1 is this way, y equal to 1, y equal to 2, y is equal to 3, we have this. Similarly y is equal to minus 1, y is equal to minus 1, and y is equal to minus 2, y is equal to minus 2. Okay, y is equal to minus 2. Now try to understand one thing. Let us suppose if my x value is lying in between 0 and 1, means if I take any value in between 0 and 1, the answer would be 0, correct? If I take 0 and 1, definitely integer part x value of that any value which is in between 0 and 1 is going to be 0. Means whenever x is changing from 0 to 1, the integer part x function is actually 0. Okay, so let me change the thickness slightly. Okay, so now you see this is 0. Now here you need to maintain one point very carefully. This graph should not touch this x is equal to 1 line, because there is no equality sign here. Okay, so that's why this small green line which I have drawn here should not touch this x is equal to 1. Similarly, for any value of x between 1 and 2, the value of integer part x is 1 actually. Okay, similarly between 2 and 3 it is 2, between 3 and 4 it is 3. So the green colored ones are the graphs here. Okay, so 1, 2, 3, minus 1, minus 2, like this. Okay, similarly here on the left side it begins with minus 1 and it won't touch 0. Similarly here also, this is how the function comes out. Okay, so this is the graph of integer part x function, and you can understand one thing why this is called step function, because if you see these are like a steps. Okay, so that's why it's called the step function. And one very important point I'd like to tell you at this point, if I say limit extends to a integer part x, this value does not exist if a is integer. If a is integer. Now let us suppose if a is not an integer, then definitely this limit will exist. Okay, but why this exactly? Means if I keep some integer value here, 2, 3, 4, something like that, why this limit does not exist? Because you can see one thing, left limit. If you talk about left limit, limit extends to a minus integer part x. So tell me one thing, whenever I am writing x tends to a minus, x is more than a or less than a. Look, in neighborhood concept I have told you, if this is your a, then this region is your range of a plus, and this region is the range of a minus, correct? So if you see, whenever I am talking about x tends to a minus, means x is somewhere here, which means x is less than a. Now whenever x is less than a, definitely x is less than a, which means a minus 1, something like this, correct? So whenever x is in between a minus 1 and a, then definitely this is the integer part value of x. So this value is going to be a minus 1. And if you calculate the right limit, limit x tends to a plus integer part x. So this, if you take, now x is in this range, so a is actually less than x. Okay, so a is actually less than x, which means x is less than a plus 1. So in that case, integer part x value is capital, this small a, and these two are not equal. So definitely this implies limit does not exist. Limit does not exist actually here. Okay, so limit does not exist basically here. Okay, so you see, whenever this is an integer, limit does not exist. But let us suppose if a is not an integer, then limit will exist. How? Look here. Let us suppose if I take a point somewhere here, for example. Let us suppose if I take a point somewhere here, for example. Okay, so at this point, on the right side and on the left side, in both the cases, the function is same. It's 1, and also here also this is 1. So that's how, whenever x is in between two natural numbers or integers, you can say this limit will exist. But let us suppose if I take exactly 3, left side the value is 2, you can see this is 2, right side the value is 3. Okay, so that's why whenever exactly when the point is at integer, limit does not exist, because right hand and left hand limits won't be same actually in that case. Okay, so with this understanding, we will see some standard limits. Let us see one thing which is called L'Hospital. So one very important rule actually. Okay, so L'Hospital's rule. L'Hospital's rule. You can apply this rule only when you have this 0 by 0 or infinity by infinity forms. Okay, this rule can be applied only under these two cases, 0 by 0 or infinity by infinity form. So let us see here. If limit extends to a, f of x by g of x, if this value is giving you 0 by 0 or infinity by infinity. So what's the meaning of this? Let us suppose when you substitute x is equal to a in this f of x, you are getting 0. Similarly, when you're substituting x tends to a, again this is also getting 0. So you will get 0 by 0 form. For example, limit x tends to 0, sin x by x. Okay, so when you substitute 0, sin 0 is also 0, x is equal to 0, will make denominator also 0. Okay, so under such cases, or it can also give you infinity by infinity. For example, you can see log x divided by some other function, say tan some function such that it gives infinity by infinity. Okay, so if you give some if this comes out, then limit extends to a, f of x by g of x. This can be written as limit extends to a, f dash of x divided by g dash of x. Okay, so this value is not equal to 0 by 0 or infinity by infinity. 0 by 0 or infinity by infinity. So let us suppose if that value is also coming to be 0, sometimes it happens, you will get if limit extends to a, f dash of x by g dash of x. If this value is same as limit extends to a, means if this is again getting equal to 0 by 0 or infinity by infinity, then limit extends to a, f dash of x by g dash of x. This value can be written as limit extends to a, f double dash of x divided by g double dash of x. Okay, and of course this should be again not 0 by 0 or infinity by infinity. If again this is also coming to be 0 by 0 or infinity by infinity, you will go for one more differentiation, limit extends to a, f table dash of x by g table dash of x. So that's why we write, and so on. This same circuit will follow, and so on basically. Okay, so this is one very important very powerful rule actually in calculus. Okay, because many times it's quite common we end up with these two ratios, so then we'll break the tie with using this L'Hospital's rule. Okay, so let me give you some standard limits. Some standard limits let me give you here. So some standard limits, let us see. First limit, very friendly limit known to you, limit extends to a, x power m minus a power m by x minus a. So if you see, we are going to get m times of a power m minus 1. Okay, so second, limit extends to a, x power m minus a power m divided by x power n minus a power n. So this value is going to be m by n times of a to the power m minus n. Okay, look, both results you can get using the L'Hospital rule, because if you substitute x is equal to a, this comes to the form 0 by 0 and this also comes to the form 0 by 0. So if you differentiate one time and if you substitute x is equal to a in the differentiation, you will get these results, okay, in both the cases. Okay, now third, limit x tends to 0, sin ax by x is equal to limit x tends to 0, tan ax by x is equal to a actually. Okay, so both these limits will be equal to this value which is a here. So fourth, limit x tends to 0, again using L'Hospital you can get this, x tends to 0, 1 minus cos x, cos ax, let us write cos ax by x square, this is equal to a square by 2. Okay, so again L'Hospital, if you apply you will get same this a square by 2, means you can see if you put 0, cos 0 is 1, so 1 minus 1 is 0 divided by 0. This division is for completely 1 minus, so you can get 0 by 0 form. So if you apply L'Hospital rule you will get a square by 2 here. Okay, next, you have a lot of limits basically. Limit x tends to 0, 1 plus ax whole power b by x, this value is going to be e power ab. Similarly, this value, limit x tends to infinity, 1 plus a by x whole power bx, this value also it gives you e to the power ab. Okay, so in these two cases basically I would like to spend a moment here. In these two cases actually if you substitute x is equal to 0 you will get the form 1 power infinity, correct? So 1 power infinity value is not 1. Okay, so please keep this in mind. Many people have this misconception that 1 power infinity is 1. No, because multiplication means if you go to fundamentals, mathematical fundamentals, multiplication is defined only when you can start the multiplication and stop the multiplication. Means basically let us suppose if I add 2.4 into 5 into 8 into some numbers and after that if I stop I should locate the ending of the multiplication. Okay, but when I hit 1 power infinity, 1 into 1 into 1 into, and I don't know where it stops. Okay, infinity is basically a symbol for denoting very large number and I don't know what is the exact value of that large number. So that's why this 1 power infinity is not equal to 1, because we cannot stop the multiplication. Understood? So that's the reason 1 power infinity is not equal to 1. It's indeterminate form basically. Okay, so whenever you'll get indeterminate forms in powers, means 1 power infinity, 0 power infinity, 1 power infinity, all these things. So let us see. Limits giving indeterminate forms in powers. Limits giving indeterminate forms in powers. Limits giving indeterminate forms in powers, let us say, means basically if you see you will get things like 1 power infinity, 0 power infinity, infinity power 0, infinity power infinity, these kind of things basically. Okay, so whenever you are getting these things, look, there is one standard procedure which is called the 2L procedure. Okay, so we'll write apply 2L procedure, apply 2L procedure. So what is this 2L procedure? 1L stands for log, second L stands for L'Hospital. L'Hospital rule. Let us see how we are going to do it. Okay, so let us take this limit. For example, limit x tends to a, sorry, x tends to 0, you can say x tends to 0, 1 plus ax whole power b by x, for example, let us say. So obviously this gives you 1 to the power infinity form. A and b are some constants. So whenever this is giving you 1 power infinity form, look, this is equal to, now what we assume is take y is equal to, for example, 1 plus ax whole power b by x. So you will take the function as some variable y, then apply log on both sides. The first L we are applying, apply log on both sides, apply log on both sides. So when you apply logarithm on both sides, this gives you something like log y to the base e is equal to, now if you apply logarithm to this, log of 1 plus x whole power b by x, so this b by x can be written separately outside, log 1 plus ax to the base e, this is what you will get. Okay, so now if you see, if you apply the limit basically on both sides, limit x tends to 0 log y to the base e is equal to limit x tends to 0 b by x into log of 1 plus ax to the base e is what you have here. Okay, now you can observe one thing. Log and limit both are transferable functions, means if you apply log to this y and then if you apply limit, or if you first apply limit and then you take log of that whole value, both remain same. So this expression on the left side can be written as log limit x tends to 0 y to the base e. This is what you can write here. Coming to this, b into what you have, limit x tends to 0 log of 1 plus ax to the base e divided by x. Now if you substitute x is equal to 0 in this equation, log 1 is 0, this denominator is also 0, so that's how you'll get 0 by 0 forms. So now you can apply L'Hospital rule to calculate this limit. How you can calculate, b into, if you differentiate this function, 1 by, or limit x tends to 0 1 by 1 plus ax into, because differentiation of log is 1 by that function, into the inner differentiation of this is a divided by differentiation of x is 1. So when you substitute x is equal to 0, this value is going to be 0. So you have ab is what you have. Okay, so this log value is ab, which means I can write limit x tends to 0 y, and what is the value of y? Nothing but this function. So 1 plus ax whole power b by x. So this value is going to be e to the power this term, so e to the power ab. This is how you will evaluate the limits. Okay, any power form you will get, if you get 0 power 0, infinity power infinity, any power form, if your indeterminate form is in terms of powers, then definitely this 2L procedure is going to help you out. So you apply log and then you apply L'Hospital, then things get settled. Okay, so but again I would like to give one technique for the first indeterminate form, means this form. Okay, whenever things are in 1 power infinity form, I'll give you some technique. Look, what is that technique? If limit x tends to a, f of x power g of x, let us suppose you have power of two functions and this is giving you 1 power infinity form, then limit x tends to a, f of x power g of x, this value is actually equal to e power limit x tends to a, g of x into f of x minus 1. Okay, so this is how you will get this. Okay, of course I can show you that using the same 2L procedure, but right now I'm not doing the derivation and all, I'm just giving you this formula. Okay, so if there is some power of functions f of x power g of x, and if you are getting this 1 power infinity form, then definitely this limit x tends to a, f of x power g of x can be calculated using the result. Okay, now for example, if you see this is a 1 power infinity form, you have applied 2 L's, one logarithm and one L'Hospital to get the result. But let us see if you get the same result using this technique. Okay, so if you see limit x tends to 0 1 plus x whole power b by x, this is the limit that you have. Okay, so this is straight away giving you 1 power infinity if you substitute. Okay, so this implies limit x tends to 0 1 plus ax whole power b by x, so this value is equal to e power limit x tends to a, so limit x tends to 0 g of x, which is b by x, into f of x minus 1, so f of x is 1 plus ax minus 1. Okay, so here if you can cancel out this 1 and 1, this is equal to e power limit x tends to 0 b by x into ax is what you have. Now we can cancel this x and x term here, so e power limit x tends to 0 ab, no x to substitute, so this is directly ab. That's how you will get the result of this limit as e power ab when you apply this. Okay, so this is one very fast track rule in calculus, basically, that whenever things are of 1 power infinity, look, you can apply this technique only and only when it is of 1 power infinity form. Okay, you cannot apply this for 0 power infinity or something like that. Okay, so that's how it's a very useful result. And also I would like to give you one more important point, that if we are getting 0 into infinity form anywhere, for example, let us suppose if there is product of two functions, for example, say limit x tends to 0 sin x into log x is there. to the base e, for example. Okay, so then you will get 0 into infinity form, obviously. Then how you will actually do this? Okay, so you will do this as this: limit x tends to 0, log x to the base e divided by 1 by sin x, you can write this. Okay, or cosecant x, you can write this. Okay, so when you substitute 0, actually this is of the form 0 into infinity, so you don't have any direct technique, but here you can get this way: limit x tends to 0. Now this is of the form, of course, if you adjust a minus sign, this is minus of infinity by infinity form. Okay, so this limit is now in the form of infinity by infinity. So now you can apply L'Hospital rule by taking log x and cosecant x as two functions. You can just differentiate them and go for the things actually. Okay, so that's how this 1 point infinity form is actually a bit important for you. Okay, and I would like to give you one more result, one more standard limit. That limit is how many we have given you? Okay, some number, 7, let us say 7. Limit x tends to 0, 1 power x, or you can write a power x plus b power x by 2 whole power 1 by x. So again, this is of the form 1 power infinity. So if you see, the answer is going to be square root of ab. Okay, so you are going to get square root of ab basically here, because you can see when you substitute 0, a power 0 is 1 plus b power 0 is 1. So 1 plus 1 is 2, 2 by 2 is 1. So this total bracket gives you 1, and this 1 by x gives you infinity form. So if you see, if you simplify e power limit x tends to a and all, you will get square root of ab basically. Okay, so square root of ab is the correct answer for this. Similarly, if you have one more, for example, limit x tends to 0, a power x plus b power x plus c power x by 3 whole power 1 by x. So this value is going to be cube root of abc. This is what you have here. Okay, so these are the limits. Some similarly, if you have 1 power x plus 2 power x plus 3 power x and so on n power x, then this is nth root of n factorial basically. Okay, so because there are n values and product of 1 into 2 into 3 and so on till n gives you n factorial. So nth root of n factorial is what you will get in general. Okay, now I'll give you one more. Okay, fine, these limits are generally the limits that we use in day to day, but I would like to give you one special kind of limits, because sometimes again you have some gate questions on that. So look, I'll give you limit x tends to a, or x tends to infinity, you can say limit x tends to infinity, limit x tends to infinity. Okay, before this I would give one limit here. Look, 9, limit x tends to 0, x into sin x, or you can say x into sin x. Okay, this is anyhow 0 known to you, sin 1 by x, let us say. Okay, so this is x into sin 1 by x, because 1 by x is infinity, so x into sin 1 by x. Okay, now when you write x into sin 1 by x, look, the answer for this is straight away 0 actually. Why it is 0? Because you can see 0 into some finite value in minus 1 comma 1, correct? Whatever might be the value of x, this value is always some finite number which lies in between minus 1 and 1. So 0 into a finite value in minus 1 comma 1. So that's why if you see 0 into some finite number will always give you 0 actually in that case. Okay, so that's why this limit is basically 0. Okay, now let us come to this infinity thing. So limit x tends to infinity, a naught into x power m plus a1 into x power m minus 1 plus a2 into x power m minus 2 and so on, am, which is some constant, plus f of x divided by this, divided by b naught x power n plus b1 into x power n minus 1 plus b2 times x power n minus 2 plus and so on, plus bn, let us say, plus g of x, where f of x comma g of x are finite valued functions. G of x are finite valued functions. Finite valued functions. So what's the meaning of finite valued functions? Finite valued functions means basically whatever the value is placed in, whatever the value is substitute in place of x, this f of x and g of x are always some finite numbers. Okay, for example, you have just seen, if I put sin x and cos x here, whatever might be the value of x, these two are always finite. Sin 2x, cos square x, all these values, basically all these are finite, some finite functions. So that's why if you see, if these are finite functions, then this limit is equal to 0 if m less than n, a naught by b naught if m is equal to n, infinity if m is greater than n. Okay, so these are very important results, because if you see many times in exams you will encounter questions like this. Of course, I'm not proving this again, I'm not showing the derivation of this. It's very simple. You need not call this derivation. If you take x power m and x power n here, then if you put x is equal to, if x is tending to infinity, 1 by x tends to 0. So if you substitute and all, you will get this three results actually. Okay, why I'm telling you this? In exams you will get questions like this: x tends to infinity, x square plus sin x by x square plus cos 2x, something like this they'll give you. Okay, so if you see, these two are finite valued functions, and here the coefficient is 1, here also the coefficient is 1, and these powers are same. M is equal to n. So in that case, if m is equal to n, the value of this limit is a ratio of these coefficients, so 1 by 1, which is 1. That's it, finished. Okay, so that's how actually this result is actually helpful for you. So basically this is one very good limit actually. Okay, means this limit is actually one very some powerful kind of limit, because many questions you will be able to solve directly here. Okay, now I'll give you one limit here again. Limit x tends to 0 1 by x, this value does not exist. Okay, this does not exist, because you can clearly see if you draw the graph of that. In yesterday's class I have given you when sin x by x I am drawing. So if you see, if this is something like this, 0 x, let me slightly, okay, anyhow my point of interest is only till this point. So this is minus x, y and minus y. Then you know one thing, if I draw y is equal to 1 by x graph, it looks like this. Here it looks like this, and here it looks something like this, correct? So we can see at x tends to 0 plus, means basically in this right neighborhood the value is plus infinity, in the left neighborhood the value is minus infinity. That's why left limit and right limit both are not same, so that's why this limit does not exist. Okay, so I will stop the video here. Thank you. Okay, so now let us continue after this. So I've given you these results basically in the case of limits. Okay, now let us move on to one very important result again in limits, that if limit x tends to a, f of x is equal to 0, for example, then limit x tends to a, f of x power f of x, this value is equal to 1 actually. Okay, and of course please make a note, 0 power 0 is not equal to 1 actually. Okay, this is 1 not because of 0 power 0 is equal to 1. There is some different logic. Again, you will get 0 power 0 form, then you need to apply two L's, one logarithm and one L'Hospital, and after final analysis you will get 1. Okay, but this is not because of the reason that 0 power 0 is actually 1. Clear? Now if you write this, for example, I'm not again showing the proof because it's a short single go video. So now if you see examples, in many times you'll get these questions: limit x tends to 0, x power x. Okay, so limit x tends to 0, sin x power sin x, limit x tends to 0, tan x power tan x, tan x power tan x. Okay, similarly you will get limits like this: limit x tends to pi by 2, cos x power cos x. Okay, so cos x power cos x, and you can say sometimes they will give you something like limit x tends to a, x minus a power x minus a. So basically you will get all these forms in this 0 power 0 forms. Okay, so in all these cases this value is basically 1. Okay, so 1 and 1 actually. Okay, because this here individually x tends to 0, this function is basically 0, so this is 1. Okay, and the logic is not because of 0 power 0 being 1, but it's because of this 2L procedure. If you apply 2L procedure, first you take the logarithm, then you apply the L'Hospital rule, then you will end up with getting 1. Okay, but all these limits, since this is a short single go before the gate examination, I'm giving direct things, not derivation of this. But again, derivation is very simple. 2L, you need to apply 2L's. Okay, so in all these cases the answer remains 1. Okay, now I'll give you one very say important point, or one of the very good point. If you see, if limit x tends to a, f of x, or limit x tends to b, or extends to a g of x does not exist, means let us suppose if one of these two limits or maybe both, sometimes if they do not exist, still limit extends to a f of x into g of x may exist. F of x into g of x may exist. Okay, so how you can say this? Because I'll give you with the help of an example. You know, limit extends to 0 sin x, this is 0, you know this. Limit extends to 0 1 by x, this value does not exist, correct? This is does not exist. But if you see limit extends to 0 sin x into 1 by x, sin x into 1 by x, so this if you see limit extends to 0 sin x by x, so sin x by x, so this value is going to be 1 actually. So if you see individually one of the limits is not existing, but when you make the product definitely this value is finite. So somehow you can see even sometimes even if these two limits, one of these two, or maybe sometimes it can happen that both also need not exist but their multiplication can exist actually. Okay, so this is one important thing actually here. Okay, now coming to differentiation, I would like to give only one point because we have talked already a lot about differentiation. So now if you see mod x function, this function is generally important. So mod x is continuous for all x belongs to R, but it is not differentiable. It is not differentiable at x is equal to 0. At x is equal to 0. Okay, means basically if you take this function mod x, if you take this function mod x, then you know we have seen so if you see this is the function, so y is equal to x, y is equal to minus x. Okay, 0 x minus x y and minus y. Now if you see carefully here, I am telling you this function is not differentiable at this location x is equal to 0. Okay, and generally I'll tell you one thing, any function at points where it is having sharp edges, for example if you see this is a sharp edge, correct, it's not going smoothly like sin x curve, it has a sharp edge. Okay, so at all the points where there are sharp edges geometrically, at those points functions are not differentiable. Why? I'll tell you. Look, see here, for example if I want to test the differentiability of this function at x is equal to 0, I need to check whether this limit extends to 0 f of x minus f of a divided by x minus a. This limit will exist or not, correct? Because if you see this is equal to f dash of 0 actually. So if this limit exists, then definitely I'll say the mod x is differentiable at x is equal to 0, but this limit does not exist actually. Why? You see here, if you calculate the left limit, limit x tends to 0 minus, this is mod x by x if you simplify, mod x by x. So this is equal to limit x tends to 0. I'm removing this minus here because I'm going to modify this function. Okay, look here I have kept a minus, but here I'm not keeping minus because according to this minus I'm going to change the function here. See here, when x is tending to 0 minus x is less than 0, correct? Whenever x is less than 0 means to the left hand side of this y axis, whenever x is less than 0, mod x is equal to minus x. Okay, so I have converted this mod x function as minus x because of this minus 0 minus here. Okay, so no more 0 minus here, only 0 divided by x, x is x anyhow. So if you see this is minus 1, so left side the limit is minus 1, and if you talk about the right limit x tends to 0 plus mod x by x. So this if you check limit x tends to 0. Now when this is tending to 0 plus means x is more than 0. When x is more than 0, this mod x value is actually equal to x value, and this is how you will get 1 on this side. Okay, so left limit is minus 1, right limit is 1. So basically this limit does not exist. Okay, so what's the meaning that physically this limit does not exist? This is not existing means this function doesn't have a differentiation at x is equal to 0. And also I would like to show you one thing geometrically here. You'll try to understand this. Normally this is a straight line passing through origin. So if you see the equation, this is y is equal to mx form. Okay, so y is equal to 1 into x, so slope is 1. So basically this angle is 45 degrees. How do you know it is 45 degrees? Because slope is nothing but tan theta. So 1 is equal to tan 45. That's the reason this angle is 45. And of course, due to symmetry, this angle is also 45 degrees. And these two are at 90 degrees to each other. Okay, now if you see y is equal to mx means, and this is a straight line, slope at every point means basically this is a straight line, so slope at every point is basically 1. Okay, means in the right neighborhood also slope is 1, which means right derivative, right side derivative is +1. You can see the right limit means basically if you calculate this derivative on the right side, your answer is 1, because geometrically this is equal to y is equal to mx form. Okay, and also on the left side, this is the equation with the slope m is equal to -1. So that's why if you calculate the left hand derivative, you will get -1 as the answer, which you got here as -1. Okay, so that's how this mod x function is not differentiable at the points x is equal to 0. But of course, you cannot see any breaking in the function, so that's why mod x is continuous for all x belongs to for all x belongs to real numbers. Means from -infinity to +infinity, this mod x function do not have any breaking in it, but obviously it is not differentiable. Clear? Now let us go for the next part. Normally I'm giving you one point which could help you out. Mod f of x, and of course f of x is polynomial functions. Okay, so or trigonometric functions, anything, it should not have denominator basically. Okay, the discontinuity is not because of the denominator but because of the function itself. So mod f of x is not differentiable at the points, is not differentiable at the points, is not differentiable at the points where f of x is equal to 0. What's the meaning of this? Look, example, I'd like to talk about one example here. Example, mod x square minus 3x plus 2. If you take this function, for example, okay, if you take this function, mod functions are continuous everywhere, but this function is not differentiable, is not differentiable at x is equal to 1 and x is equal to 2. Why at x is equal to 1 and at x is equal to 2? Because at x is equal to 1 and x is equal to 2, this function which is inside the modulus becomes 0. Okay, so whenever you have this function, means if you identify those points where the function inside the modulus is 0, in such cases these functions won't be differentiable. Clear? And at that point the functions will generate a sharp edge. Okay, why sharp edges are dangerous? Look, means they are not differentiable. Look, I'll tell you. Let us suppose if you have a function like this, some x-axis, y-axis I have it on, for example, so 0 x y like this. Now what happens is, look, let us suppose you got a sharp edge like this. Okay, let me draw more clearly. Like this, you got a sharp edge at some location. Okay, so when you got a sharp edge, if this is the point, if you take the left side, the tangent to this curve will be something like this. Okay, so this angle will be more than 90. Similarly, if you draw a tangent in the right neighborhood, means somewhere here, if you take a tangent, this will be, you can see this angle will be less than 90. Okay, so one slope will be negative and another slope will be positive, like you have seen in mod x case. Whenever there is a sharp edge, at the sharp edge on the right hand side you will have some positive slope, on the left hand side you may have some negative slope. That's the reason why these two slopes, means right slope and left slope, or you can say right derivative and left derivative, these two won't become equal generally whenever you have a sharp edge. Okay, so that's why all these functions, they generate sharp edges at these points. Now similarly, mod sin x is not differentiable, mod sin x is not differentiable at x is equal to 0 plus or minus pi plus or minus 2 pi, all these points, because you see all these points are the points where this sin x function is basically equal to 0. Okay, so at all these points these functions are not differentiable. Clear? So with this we generally finish this differential calculus. Okay, and basically now we'll see some applications of this differential calculus, like we'll talk about some applications of differentiable calculus like mean value theorems, Taylor series, concept of maxima and minima, all these things. Okay, so let us quickly start mean value theorems. Okay, so mean value theorems, mean value theorems. Okay, so these mean value theorems are of actually very much important. I'll tell you why and all. There are many concepts where we use this mean value theorem. For example, if you see, the concept of maxima and minima is also one of the consequences of this mean value theorem, okay, which is of course a whole theorem we'll see now. And we have a lot many applications of this mean value theorems. Okay, look, let me ask you one question. You can pause the video, we'll see some general example, some normal example. Now let me try to make you understand this thing. Look, let us suppose there is a straight out. On this straight out, let us suppose they have kept some speed limit, some 60 kilometers per hour, let us suppose. Okay, so 60 kilometers per hour is the speed limit, for example, speed limit. So, and they told you, if you cross 60 kilometers per hour at any point on this road, you will be charged, you will be fined actually. Okay, now let us suppose there are speed guns. There is one speed gun here and also another speed gun here. Now let us suppose if this distance between these two is some 2 kilometers gap they have kept, for example 2 kilometers gap they have kept, in 2 kilometers span they have kept some 2 speed guns. Okay, now, or let us say 20 kilometers, generally they have placed some 10 kilometers within that range, so 10 kilometers, let us say this is in 10 kilometers. Now whenever you identify that there is a speed gun, what we'll do, intentionally we slow down the vehicle, correct? We apply some brakes and we make sure that no fine gets imposed on us. So what we do, we will try to slow down here. Okay, so I came very fast, but then I slowed down here very slowly. I'm acting so good that people don't recognize that I am moving above 60. Similarly, in the main range, I'm moving very fast again, and at this point again I am slowing down to 30 or 40, let us say. Now we assume that since we maintained some speed which is below that speed limit at these two speed gun locations, there is no fine on us, but actually we can still be fined. How come? Look, let us suppose if the time taken to cover these two points is basically, let us suppose 8 minutes you have covered. In 8 minutes you have gone this 10 kilometers, which is normal speed. If you drive at 70 or 80, you will easily cross 10 kilometers in 8 minutes. Okay, so now if you see, if you observe one thing, you can cross these 2 points only in 8 minutes, only at least at some location if you have crossed that 60 speed. Yes or no? Means definitely here you maintained 30, here also you maintained 30 kilometers per hour, but definitely somewhere in between you have definitely crossed this speed. That's the reason why within 8 minutes you have cleared this 10 kilometers. Yes or no? Because if you have traveled below 60 kilometers per hour continuously, it would have taken you more than 10 minutes, but this vehicle number is registered here, and in less than 8 minutes this vehicle number is again registered here. That means meanwhile this person has crossed the speed limit of 60, correct? This can be identified using mean value theorems. Okay, look how I'll tell you now. So first let me give the concept of this Lagrange's mean value theorem. So the first fundamental theorem is Lagrange's mean value theorem. Lagrange's mean value theorem. So let's see what is this Lagrange's mean value theorem. Lagrange's mean value theorem. If f of x is continuous, if f of x is continuous on closed interval a comma b, and it is differentiable, and it is differentiable on open interval a comma b, then there exists a value c, such that x belongs to c, x such that c belongs to a comma b, and f dash of c, there exists at least one value, right? At least one value c. Okay, we'll write at least one value c. At least one value c such that c belongs to a comma b, and f dash of c is equal to f of b minus f of a divided by b minus a actually here. Okay, so this formula is actually important, and we'll see how this formula is coming. What is this f of b minus f of a by b minus a? Let us try to understand this. Okay, so what we are trying to do is, look, f dash of c is equal to f of b minus f of b a by b minus a. So what is the meaning of this actually? Look, if you take this curve, for example, this is your x-axis, this is your x-axis, and let us say this is your y-axis, for example. So 0, x, minus x, y, and minus y. So let us suppose you have some curve like this, some random curve. So this is y is equal to f of x, for example. So this is y is equal to f of x, let us say like this. Okay, now try to understand one thing. Let us suppose if this point is x is equal to a, and if this point is x is equal to b. Okay, so let us suppose if this point is x is equal to a and this point is x is equal to b on x-axis. Okay, so now you can understand one thing. If this is x is equal to a, then definitely this value is f of a and this value is f of b, correct? So you can write, so you can see this is f of a and this is f of b. So if you take this point capital A, for example, and this point is capital B, then if you write the coordinates of a, what are the coordinates of a? This point is at x is equal to a and y is equal to f of a. So this point has the coordinates of a comma f of a. Similarly, the coordinates of this point is b comma f of b, basically here, correct? B comma f of b. So if you connect these 2 points with a straight line, so you will get that straight line. So what is slope of AB basically? So slope of AB is equal to, you see, this is a straight line passing through 2 points, a line segment passing through 2 points, a comma f of a and b comma f of b. So y2 minus y1 divided by x2 minus x1. Okay, so this is slope of AB. Okay, and if you see, this slope of AB is nothing but the right hand side of the equation that we wrote earlier. So this right hand side of the equation is f of b minus f of a by b minus a. Next, what is f dash of c? Means, look, if you take this point, for example, if you take this point, say this point, for example, x is equal to c, this point is x is equal to c. So what is f dash of c? F dash of c is nothing but slope of the tangent to this curve at this point, yes or no, correct? So if you see, this is your tangent at x is equal to c, and at x is equal to c, this is the tangent basically. So the slope of the tangent to this curve at x is equal to c is given by f dash of c, we have seen. So we say that whenever there is a continuous function like this and differentiable, at least in between x is equal to a and x is equal to b, in between these 2 points, x is equal to a and x is equal to b, there exists at least one point such that slope of the tangent at that point is equal to slope of this line AB. Okay, and there can be many points depending upon the nature of the curve. Okay, so there can be one more point here. Okay, so if slope, if there are 2 parallel lines, means so if slopes are equal, those lines look parallel. Okay, so means the tangent and the line AB, the line segment AB, both are parallel to each other. Okay, so there can be many points like this. So that's how f dash of c is equal to f of b minus f of a by b minus a actually here. Okay, so the geometrical meaning of this Lagrange's mean value theorem is, you call this LMVT sometimes. Okay, I think I didn't give you this, LMVT, it's called LMVT, Lagrange's mean value theorem. So the geometrical meaning of this Lagrange's mean value theorem is, whenever a function f equal to f of x is continuous from a to b and of course differentiable, then in between a and b there exists at least one point, such that f dash of c, means the slope of the tangent at some location c, is equal to f of b minus f of a by b minus a, is equal to slope of the line segment joining AB basically. Okay, so this is what you have. Now how this is related to this example that I'm talking, this is the displacement and we know the time, correct? So velocity is nothing but a rate of change of displacement, correct? So which means nothing but differentiation of this speed. Okay, so s dash, if I give distance with respect to time, s dash of t is nothing but a velocity. Okay, so now if you calculate for this example, at least at one point between time t is equal to 0 and t is equal to 8 minutes, time t equal to 0 and t is equal to 8 minutes, at least at one point your velocity is equal to f of b which is 10 kilometers, because if you take this as 0 kilometers and this is 10 kilometers, then 10 kilometers minus 10 kilometer per hour minus 0 kilometer per hour, because if you see at this location, if you it is 10 kilometers and this is 0 kilometers. If you take for example, then 10 kilometers minus 0 kilometers divided by, you can see 8 minutes. 8 minutes means 8 by 60 hours. Okay, so these many hours, so 600 by 8, so 600 by 8 is actually more than 90. Okay, so at some location, because if you see 9, okay, 9, it's not 90, 90 is very high. 7 8 8 8 are 64, you can say. So 5 8 are 40, 6 8 are 48, 7 8 are 56, so 8 8 are 64, so it's something more than 75 kmph. Okay, so if you see, this is something more than 75 kmph. So at least at one point definitely you have crossed a speed of 75. So that's how the people come to know that using this mean value theorem, at least at one point you might have definitely crossed the speed of 75 kilometers per hour. So definitely you will be fined. Okay, so this is some this is the somehow you generally use this mean value theorems, not only in this example, in many examples actually you will take the mean values and all, but this is one simple common example that we all deal with, so that's why I have given you this. Okay, so this analysis of mean value theorem, Lagrange's mean value theorem, tells you that at least at one point definitely this person has crossed a speed of 75 kmph. Okay, so that's how you are sure, because people when they come to fight with you that, sir, at both speedometer, at both the speed guns I have traveled at 30, how do you know that I am traveling at 75? You can tell them, make them sit, take one board, write Lagrange's mean value theorem and explain this. Okay, then they will get convinced and they'll pay the fine if you become a traffic inspector. Okay, fine. Anyhow, look here, so Lagrange's mean value theorem. Now, so this is Lagrange's mean value theorem. Basically the slope of the tangent at one location, at least at one location, is equal to slope of this line. Okay, so now actually if you see, this is the generalized theorem of one very earlier theorem than this. Okay, so there is something called a Rolle's theorem which came much before this Lagrange's mean value theorem, but later people realized that Rolle's theorem is one special case of this Lagrange's mean value theorem. Okay, so that's why this Lagrange's mean value theorem is taken as the most fundamental theorem, but actually Rolle's is the previous or the most oldest mean value theorem actually. Okay, so let us see what is this Rolle's theorem. Rolle's theorem. Okay, so let us see what is this Rolle's theorem. Now this Rolle's theorem tells you that, again the same story, if f of x is continuous, if f of x is continuous in AB and differentiable in open A comma B, then, and you can write one more condition, and if f of A is equal to f of B, f of A is equal to f of B, then there exists at least one point C, at least one point C such that f dash of C, such that f dash of C is equal to 0. Okay, and you can write one thing, such that C belongs to A comma B, C belongs to A comma B, because C should be always in between A and B, and f dash of C is actually equal to 0, which gave the concept of maxima and minima, and this is the fundamental theorem for the concept of maxima and minima. Okay, because you know at any point if there is maxima or minima, the differentiation at that point is 0 basically. Okay, we'll see how that's happening. Look, see, let us suppose if I draw some coordinate system, again x axis and y axis, say something like this, this is x, this is y, x minus x, y minus y. Okay, now you see here, let us suppose if there is some function like this, some function like this, some function like this, for example. Okay, now in such case, here if you plot the coordinates, this is x is equal to A, this is x is equal to B, x is equal to B, this is x is equal to B, x is equal to B, and we know, means we have assumed this assumption that f of a and f of b both are same, means these 2 points are on the same horizontal line, correct? So if you see this point, means if you write the coordinates of this point has the coordinates a comma f of a, and this point has the coordinates b comma f. This point has the coordinates b comma f of b actually here, okay? And you can see capital A, capital B, for example. Then if you see the slope of this line is 0, correct? Because the line connecting these 2 points is horizontal this time. So whenever the line connecting those 2 points is horizontal, then definitely, you know, the angle made by x-axis is 0, x-axis and this line both are parallel, so slope is 0 straight away. So this is the point C. This is the point. This is the point C. This is the point C actually. So this is the point x is equal to C, and you can understand one thing, that here if you draw the tangent, again this tangent will also be horizontal. The graph need not be like this, it can be a upper half also, means basically if you can see this, I can represent the concept of maxima also, okay? So at stationary points, basically the values of x where this differentiation is 0 are called stationary points, and to identify whether you have a maximum or minimum, you need to go for something called second derivative test. I'll talk about it when I go to concepts of maxima and minima, okay? So right now my main intention is to tell you that whenever there is some function like this such that the functional values are same, definitely there exists a point where this f dash of c is actually equal to 0. Clear? So this is basically the foundation for the concept of maxima and minima, of course, okay? So we'll go for that in a moment, but this is Rolle's theorem, okay? Now Cauchy's mean value theorem is again something like this. Cauchy's mean value theorem. Cauchy's mean value theorem, which is generally written as CMVT, Cauchy's mean value theorem. And of course, if you see this Rolle's mean value theorem, sometimes it is known with the name RMVT, Rolle's mean value theorem, okay? So Rolle's mean value theorem, and this is Cauchy's mean value theorem. So Cauchy's mean value theorem is something like this. If f of x comma g of x, this is nothing but application of Lagrange's to 2 functions simultaneously, okay? If f of x comma g of x are two functions that are continuous in a comma b and differentiable in open a comma b and differentiable in open a comma b, then there exists at least one point C. There exists at least one point C such that C belongs to a comma b and g dash of C by f dash of C. This is equal to g of b minus g of a divided by f of b minus f of a actually, okay? So this is how we have the result. Basically g dash of c by f dash of c is equal to g of b minus g of a by f of b minus f of a. This is very simple. If you apply Lagrange's individually to g of x, you will get this value. G dash of c is equal to g of b minus g of a by b minus a. Similarly for f of x, if you apply this, you will get this value, f of b minus f of a divided by b minus a, okay? And here you will cancel out these two values basically. So that's how you get this result. It's basically for Cauchy's mean value theorem. Because many times I'll tell you one thing, it's when you plot a graph, it's not mandatory that always your horizontal axis takes the value y is equal to x, okay? You can take y is equal to some other function also. For example, many of you might have drawn this log graphs, okay? You know, I'll show you. Basically I'll show you with the help of some Google. So log graphs, okay? Log graph paper. So if you see, normally if you see, this is how the log graph paper looks like, okay? Here some readings are given, so I'll display this picture better. Okay, I think some internet is slow today, maybe some issue, but right now my intention is to tell you that, okay, something is opening. So normally when you take this axis, it's need not be x always, okay, it can be some other values also, okay. So for example, here you can see this is 10. If you take this paper in reverse order, this is 10 power 1, 10 power 2, all this. Yeah, here if you see this y-axis, or if you take this x-axis, and it means basically if you take two axes, the horizontal axis need not be always the x-axis. I mean, take the function y is equal to x, okay. For example, in log graphs, what happened here, you have the log, means the variation is in terms of log. Here you can plot some other parameter, for example voltage or something, coarseness of grains and all. So if you see here, you can plot some quantity which is of your interest, and here this scale can be varied according to log, okay. So that's how you need not always plot x and y f of x. You can plot some f of x and g of x functions simultaneously on a graph in a 2D, okay. So that's how this Cauchy's theorem is basically application of this LMVT for two functions, okay. So next, let us go for Taylor series. But before going for Taylor series, I would like to give you two very good points actually coming to mean value theorems. What are they? Look, I'll tell you. See, I'll give you one question. You can pause the video and you can solve this. The value of C estimated using mean value theorems. The value of C estimated using mean value theorem for the function f of x is equal to e power minus x into sin x minus cos x, in the interval say for example pi by 4 you take, 5 by 4 to 5 pi by 4 you take, okay, 5 pi by 4 for example, okay. So let us suppose in this interval, what is the mean value C calculated using mean value theorem? Options also will give you 0, pi by 2, pi, 3 pi by 2, 3 pi by 2 actually, okay. Now so this is the mean value, so mean value theorem basically, and they are asking you what is the value of C. This is one very good question actually. I want to tell you one very cautious point of this mean value theorems with the help of this question. Look, what is that point? Solution, if you try to solve this, then you know f dash of C is nothing but f of B minus f of A divided by B minus A. Now try to understand this. F of A means basically f of pi by 4. So this value is straight away 0, because of course e power minus pi by 4 is there, but sin pi by 4 and cos pi by 4 are same, so definitely this bracket is going to give you 0. So 0 into some value, it is 0. Similarly, f of B, if you calculate f of 5 pi by 4, so this value is also going to be 0, because if you check, if you check basically again at 5 pi by 4, these two values are same, both are negatives of course, but both these values are same. So e power minus 5 pi by 4 into some quantity is again 0. So what is f dash of x? If you calculate first function into derivative of second function, so differentiation of sin x is cos x minus differentiation of cos x is minus sin x. So this is the case, plus differentiation of first function, so minus e power minus x into second function, which is sin x minus cos x. So if you simplify this, e power minus x, if you take out, then cos x plus sin x, then minus of sin x gives you minus sin x, and minus of minus gives you plus cos x. So this is what you have. This sin x and sin x gets cancelled. So 2 times of e power minus x into cos x is what you will get here, correct? Or did I do some mistake here? So this is sin x, so minus e power minus x into e power minus x into sin x minus cos x, and yeah, I think it is fine, correct? Or else is there some mistake here? We'll do one thing, we'll take the function as e power x, because I have to show some result here, so some important thing, e power x into sin x minus cos x. So this differentiation will be e power x, here also it is e power x. So this result changes slightly. So see here, we'll see e power x plus e power x into sin x minus cos x, okay. So if you take e power x common, you have cos x plus sin x minus cos x, then cos x gets cancelled, you have 2 sin x, okay. So this is the function. So what is f dash of c? F dash of c is equal to 2 times of e power c into sin c is equal to f of b 0 minus f of a 0 by pi, because 5 pi by 4 minus pi by 4, anyhow this is 0. So 2 times of e power c into sine c is equal to 0. But one thing, this e power c cannot be 0 for some finite values of c. So c is not infinity, c is some finite value here. So definitely you have to get this equation, sine c is equal to 0. So as soon as you see this equation, you write c is equal to 0 and take the first option. But actually this is wrong, because I told you along with the satisfying of this equation, there is one very important criteria, that c should also lie in between a and b, correct? If you generally miss this condition, not only you, you means not personally the one who is watching this, but in general, if you see, people miss this a point that c should lie in between a and b actually. Okay, so that's the reason why, without focusing much on that, they directly equate this sine c is equal to 0. They directly equate sine c is equal to 0, and they basically write this c is equal to 0, but which is wrong option. That's why it's given in GATE and also in many PSUs. Okay, so this is one important point. So c, when sine c equal to 0, c have many values, plus or minus pi, plus or minus 2 pi, all these values. But out of all these values, the value which lies in that interval is pi actually. Okay, so pi is the correct answer, but a is means basically 0 is the wrong answer. Why I have given you this example is because you should always keep in mind that along with satisfying this derivative condition, it should also satisfy that c lies in a comma b. Clear? So that's why it's very important. Okay, next I would like to give you one very important point. Let us suppose if you calculate this mean value, the mean value c calculated for the function f of x is equal to, say, some 9.81 x square plus some 3.14 x plus some 2.718. let us suppose they have given this function in the interval 1 by 2 comma 1 by 2 comma 1. Let us say they have given you this function. Then it's obvious, by now you might have understood, to calculate c value it is quite time taking, because the constants are 9.81 and all, and x value also some fractions are there. Okay, so 1 by 2, all these things. So if you calculate the mean value theorem using this normal procedure, you will definitely take some time. But there is a technique for quadratic functions. Okay, look, what is that technique? I'll tell you. If f of x is ax square plus bx plus some constant c, for example ax square plus bx plus c, then the mean value in the interval a comma b is just a plus b by 2 directly. Okay, straight away it's average of the interval, and it doesn't depend upon this coefficients capital A, capital B, capital C. How this is happening? Look, I'll tell you. So as per mean value theorems, you can see f dash of c is equal to f of b minus f of a divided by b minus a. So what is f of a? F of a is equal to, or f of b, let us start with f of b. This is a b square plus capital B times of b plus c. And what is f of a? Capital A into a square plus b into this small a plus c. So if you subtract these two things, f of b minus f of a is equal to, this c gets cancelled of course, so capital A times of b square minus a square plus capital B times of b minus a. Okay, so this is what you have. So divided by b minus a. And what is f dash of x? F dash of x is equal to 2ax plus b is what you have. Okay, now let us substitute. Let us call this value zeta, for example, because you'll confuse between this c and capital C. So zeta, for example, so 2 times of capital A is zeta plus b. This is equal to f of b minus f of a is this value, a into b square minus a square plus b into b minus a. This value divided by b minus a. So you can see this cancels this b plus a times, and also it cancels out this term. Okay, so that's why if you see 2a zeta where zeta is the mean value, plus b is equal to capital A times of b plus a plus capital B. So capital B and capital B gets cancelled. So this implies 2a zeta is equal to a times of b plus a, and I am cancelling this capital A. Capital A is not equal to 0, because if capital A is equal to 0, this equation is no more quadratic. Okay, so it's just a linear equation. So that's why we are not taking capital A to be 0. So zeta, the mean value, is nothing but small a plus small b divided by 2 actually here. Okay, so if you see, this mean value is not depending on capital A, capital B, capital C. Okay, so it doesn't depend upon the coefficients of the quadratic equation, it just depends upon the interval values. Okay, so once you get the interval values, you just need to take the average of the interval values, and that is nothing but the mean value C for this quadratic function. So now if you come back to this example, intentionally I have given you these coefficients because once or twice they have done this in examination. So 9.81 is acceleration due to gravity, this is pi, this is e. That's how I framed this question. So basically, if you see, if you calculate mean value directly, this is nothing but 3 by 4. That's it. Okay, so you need not do the calculations like 9.81 into 1.2 whole square, nothing. Okay, so this is the thing for the quadratic functions. Okay, so that's why I have given you this example. So with this, we close this mean value theorems, and next let us quickly move on to Taylor series. Okay, so let us see the Taylor series, which is one of the very important module, Taylor series. Of course, in this video we will do one thing, because this video calculus is a vast module. In this video we will cover single variable calculus, and we'll do some other video, means the next video we'll do on multivariable calculus. Okay, so there we'll see multiple integrals, concept of maximum minimum for 2 or more variables, we'll see there. Okay, so in this video let us restrict ourselves to single variable calculus. Okay, now let us see here Taylor series. So what is this Taylor series? If a function f of x is continuously differentiable at x is equal to a, for example, means what is the meaning of that? F dash of a, f double dash of a, f triple dash of a, and so on, all the exist, then the Taylor series expansion, of f of x, about x is equal to a, is given by this function, that f of x is equal to f of a plus x minus a into f dash of a by 1 factorial plus x minus a whole square into f double dash of a by 2 factorial plus, and so on, x minus a whole power n into nth derivative of f at a by n factorial plus, and so on, infinity basically. Okay, this is a infinitely extending series. So if you see, this is how the Taylor series expansion is given, of course in single variables. Okay, so now if you see, whenever I'm writing f dash of a, that means I'm assuming x is very close to a, correct? So whenever x is very close to a, this higher order terms, x minus a whole square, x minus a whole cube, all these terms will be much smaller. So generally sometimes they are neglected, and we write this as linear approximation. So if you see, in this linear approximation, we consider the terms only till the linear degree, means here the degree is 1, from here they are higher order terms, second degree, third degree, and so on. So in case of linear approximation, we consider the Taylor series only till this value. So f of, because why? Because when we are talking about f dash of a, f double dash of a, all these things, we assume that x and a are very close to each other. So we see f of x is equal to f of a plus x minus a times of f dash of a by 1 factorial. Okay, this is where we'll end, because this is the linear approximation. This linear approximation means basically we are assuming x tends to a actually. Okay, because when x is very close to a, then all these values, higher order terms, will be neglected. Okay, so this is linear approximation. Similarly, if you go for quadratic approximation, you will consider till this point. Similarly, cubic approximation, you will consider till the third derivative. Okay, but right now if you see, we'll take the linear approximation and the series ends here. Okay, and also if you see, basically one thing, coefficient of x minus a whole power n in Taylor series expansion of f of x, in Taylor series expansion of f of x about x is equal to a, about x is equal to a, is nth derivative of f at a divided by n factorial. Okay, so this is n factorial. Now let us see, basically this is how we'll get the coefficients, okay, and linear approximations and all. Now let us see let us generate the Taylor series expansions for to the regular function sin x, cos x, e power x. Let us say these three functions, let us generate the expansions. Okay, so how these expansions look like. Okay, so first, f of x is equal to sin x. Let us suppose you have taken sin x. So what is the differentiation? Basically, look, if you write sin x, if you write this expression, f of x is equal to f of a plus x minus a into f dash of a by 1 factorial plus and so on infinity. Let us suppose if you write the infinite extending series. So tell me, about x is equal to 0, you are writing about x is equal to 0 means in the expansion you just need x terms. You need not need any term like x minus pi by 3, x minus pi by 2, nothing like that. You just need the series in terms of x, that's it. Okay, so that means this a value has to be 0, correct? If this a value is equal to 0, only in that case you will have x terms. Okay, otherwise you will have some x minus some constant terms. Okay, so we need only x terms. Now see how it's happening. F dash of x is equal to cos x. So this implies f dash of 0 is equal to 1, cos 0 is 1. F double dash of x is equal to, differentiation of cos x is minus sin x. So f double dash of 0 is equal to 0. F triple dash of x minus cos x. So f triple dash of 0 is minus 1. Similarly, fourth derivative of x, which is minus of differentiation of cos x, is minus sin x. So total you will have sin x, which means f fourth derivative of 0 is again 0. So you can understand one thing, after three derivatives the fourth derivative is again the function itself. Now let us suppose if you do differentiation once more, you will get cos x, which means this means basically this sin x, cos x, minus sin x, minus cos x, these four terms will be repeating actually. Okay, so that's how, if you see in this case, f of x means basically sin x is equal to f of 0. So sin 0 is 0. So f of 0, if you write, this is 0. So sin 0 plus x minus a, which is x, into f dash of a by 1 factorial. So 1 by 1 factorial plus x minus a whole square into f double dash of a 0 by 2 factorial. Next, plus x cube into third derivative minus 1 by 1 factorial plus and so on. This goes on. Now you can understand one thing. Can I say all the even derivatives will be 0? Second derivative 0, fourth derivative 0, again sixth derivative will be 0, which means you can see whenever even derivatives, means if you see the even power terms in this sin x expansion are, you cannot see the even power terms because the even derivatives of the function is 0. So in the Taylor series expansion you cannot see any terms with even degree. So that's why if you see, your sin x is equal to x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial and so on. This sequence, this series will actually go on till infinitely many terms. Okay, so this is the expansion of sin x about the function x is equal, about the point x is equal to 0. Okay, so this is sin x expansion. Now you have written this point many times, for very small values of x, sin x is equal to x. How do you know that? Because if you see, whenever x is very small, like for example 0.001 10 power minus 4, you can take like that. So then this x cube value will be much smaller, correct? So x power 5 is still small, x power 7 is very small. So that's why whenever x is very small. For small values of x, means x is very small, this x cube will be much smaller, and 3 factorial is division with 6, 5 factorial is division with 120, 7 factorial 5040. So all these terms will come very small. So that's how this sin x value will be almost equal to x. And also I would like to show it graphically, since we have this Desmos with us. I'll show you this graph. So see here, look, we'll plot sin x and also we'll plot x. I'll show you something here. So sin x x. So if you see, this is the graph of sin x and x. Basically the red color one, you see red symbol is for sin x, so red color one is for sin x, blue is for x. So now if you see this, look, this is x axis, okay, and this is basically some x is equal to 1 around. But now if you see very close to 0, okay, so very close to 0, if you see the red color curve and blue color curve, they are almost the same, correct? They have overlapped each other, and you can observe them as a single curve actually, okay. So that's why if you see, whenever x values are very small, the sin x and x, you cannot find any variation between sin x and x almost, okay, they are very close. So that's how graphically also you can see sin x and x are very close, but the logic behind that is because of the Taylor series, okay. Now you know why sin 0 is 0. If you put x equal to 0, every term is 0, okay. From triangles, of course, you know, when theta is very small, opposite side length comes very short, so that's why sin 0 is 0. But again, from the Taylor series also, you can observe that sin 0 is 0. So all these are basically very good interconnected things, actually, geometry, calculus, all the things, okay. So similarly, if you generate for cos x 1 minus x square by 2 factorial, this is the series you will get if you do the same procedure, minus x power 6 by 6 factorial plus x power 8 by 8 factorial, and so on, infinitely many terms, okay. So now if you calculate for e power x, you will get 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial by 4 factorial, and so on. This goes to infinity. Now once in one of the classes, students asked me, so how differentiation of e power x is e power x? You can just differentiate this, you will get, okay. So if you differentiate this, see what you will get. D by dx of e power x is equal to differentiation of 1, 0, it's a constant, plus differentiation of x by 1 factorial, 1, plus differentiation of x square by 2 factorial. 2 factorial is as it is, differentiation of x square is 2x. So 2 can cancel this 2 factorial 1 factorial times, correct? Because 2 factorial can be written as 2 into 1 factorial, so 1 factorial, plus differentiation of x cube, 3x square divided by 3 factorial is 3 into 2 factorial, so 3 gets cancelled again. Similarly, differentiation of x power 4, 4 into x cube by 4 into 3 factorial, and so on, this goes on. So you can cancel 4 again. So if you take as a whole 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial, and so on, infinity. So which is again nothing but e power x. So e power x is same as its differentiation, okay. And now if you see, generally we have this. Similarly for cos x, if you want to show it is minus sin x, anything you can calculate using the Taylor series approximations, okay. So that's how Taylor series is very useful to you. And also Taylor series expansion in general means not at a particular point. If you want to calculate at any given point, that general Taylor series is given by this expression, f of x plus h is equal to f of x plus h by 1 factorial into f dash of x plus h square by 2 factorial into f double dash of x, h cube by 3 factorial into f table dash of x, and so on, basically, okay. This goes to infinity actually. So this expression and previously at x is equal to a expression, both are same, because you have seen h is nothing but x minus a, correct? We have seen if you write x minus a tends to 0, which means x tends to a, or if you write h tends to 0, both these are actually same, correct? We have seen during the first principle of differentiation and all, both these are actually identical. So if you see, in place of x plus h, if you keep, since h is very small, you can neglect it to 0, so you'll write f of x is equal to this. As x is tending to a, you can replace this x with a plus h, x minus a by 1 factorial into, since x and a are very close to each other, you can replace this with f dash of a, all these things. Okay, basically x minus a whole square by 2 factorial into f double dash of a. So all these things are basically identical again. Okay, so that's how in Taylor series we talk some good points about the series and how the functional values are defined basically. Okay, so this is one very important part of this basic calculus and differential calculus actually. So with this we conclude this Taylor series part. Okay, so in Taylor series, if you quickly recollect, we have talked about what is the generalized expression of any expansion about a particular point a, and also we have talked about the much generalized expression. So we have generated what is the Taylor series expansion for sin x, then we have seen what are the Taylor series expansions for cos x, e power x, all these things. We have understood what is linear approximation and what are the coefficients of x minus a whole power n terms. All these things we have observed here. Okay, so with this understanding, let's move to one last part of this differential calculus, concept of maxima and minima. So let us write this concept of maxima and minima. Concept of maxima and minima. Concept of maxima and minima. So let us suppose if I give you some function f of x, how will you find the maximum and minimum values of that? Okay, so let us see. If f of x is a function, is a differentiable function, is a differentiable, if f of x is a differentiable function, then to calculate maxima and minima, I am giving you the working procedure. Then to calculate maxima and minima, look what we'll see, try to understand here. I'm giving you the working procedure. So the first point is calculate the stationary points. What are stationary points? Basically the points where the function stops, like it takes a maximum pause and it generally decreases for a while. Okay, so stationary points, which means you should calculate these points where f dash of x is equal to 0. So how many points you will get, that depends upon the function, because for example, let us suppose if I give you cubic equation, then when you differentiate it, you will get a quadratic equation, correct? When you equate a quadratic equation to 0, you will get 2 roots. But let us suppose if I give you quadratic equation and if you differentiate it, you will get linear equation, you'll have only one stationary point. So number of stationary points depend upon the type of function that I give you. So I'll show you the procedure for one stationary point. Okay, so when you have done this, let x naught be a stationary point, for example. Okay, let x naught be a stationary point. If x naught is a stationary point, then to calculate f double dash of x naught. F double dash of x naught means you need to calculate the second derivative value at this stationary point. So once you calculate this, if f double dash of x naught is less than 0, then f of x has maximum at x is equal to x is equal to x naught, and maximum value of the function is f of x naught actually. Okay, now similarly, why this is coming, look, I'll spend some time and I'll tell you. Look, let us suppose you have a function like this. Okay, so this is some function and this is the graph actually y, and let us suppose I have taken some function like this. Intentionally I am taking maximum because I want to show you the first point. So now this is the point at which you have a maximum, of course. Now why the second derivative at this point should be negative, that's the question, correct? Of course, stationary point, so you have a zero slope tangent. Just a minute. you have a zero slope tangent. That's okay. Now, why the second derivative has to be negative at this location? That's the important question. See, second derivative. If you want to talk about second derivative, means if I calculate f double dash of x naught, which is differentiation of differentiation, can I do it like this? Let us suppose I'm taking one point here, say x2, and one more point here, x1, for example. So this point is x1 and this point is x2, for example. So can I write this as f dash of x2 minus f dash of x1 by x2 minus x1? Can I write it like this? So I can write it like this, because normally if there is only single derivative, you take the functional values difference with respect to x, but if it's second derivative, you take the difference of the derivatives with respect to x. Okay, so now you can observe one thing. Let us suppose if I draw a tangent at this location x2, then this is how my tangent comes over, and if you see this angle theta 2, if I call, this is greater than 90. Similarly, if I draw a tangent at location 1, for example, say at this location, let me change the color. So at location 1, if I draw a tangent like this, if I draw a tangent like this at this location, then this value is theta 1. This is theta 1, okay, and theta 1 is less than 90. Now tell me one thing, if theta 1 is less than 90, tan theta 1 is positive, yes or no? And what is tan theta 1? Nothing but f dash of x1 is positive. Similarly here, if you consider theta 2 is negative, that means tan theta 2 is greater than 90, which means tan theta 2 is negative. Okay, so this is negative because it falls in second quadrant. So this means f dash of x2 is negative. I have shown you for this case of maximum. Okay, if you have taken the case of minimum, result should have been something different. Okay, so if you see f dash of x2 is negative minus f dash of x1 is positive divided by x2 minus x1, this is positive. So you see the total term is negative. That's why whenever you are talking about maximum, this second derivative should be negative. Clear? So this is one very important understanding, and of course normally you generally don't find this explanation and all in books, but this is a very simple explanation actually, that whenever you are talking about maximum, your second derivative should be 0. This is the reason. Clear? Now anyhow, so that's the first point. Now second point B, if f double dash of x naught. Now this I am not going to explain with this diagram and all, because it's a similar thing. So if f double dash of x naught is greater than 0, then f of x has minimum at x is equal to x naught. Okay, at x is equal to x naught, and minimum value is f of x naught actually. Okay, so this is f of x naught. Clear? So minimum value is f of x naught. Now last point C, if f double dash of x naught is equal to 0, then we can't comment on existence of maxima and minima. We can't comment on existence of maxima and minima. Such points are called inflection points. Such points are called inflection points, or sometimes they are also called critical points. So inflection points, or they are also called points of inflection, or sometimes they are also called critical points also. Look, why we can't comment on maxima and minima. For example, if you see, I'll give you two examples so that you'll get it better. Okay, so example, x is equal to 0 is a point of inflection, x is equal to 0 is a point of inflection for f of x is equal to x cube. If you take this f of x is equal to x cube, then you will understand that, for example, if you take f of x is equal to x cube, then this implies f dash of x is equal to 3x square. So if you equate it to 0, your stationary point is x is equal to 0. Now what about f double dash of x naught? f double dash of x is nothing but 6x. So this implies f double dash of 0 is equal to 0 again. So first derivative and second derivative at x equal to 0 are both zeros. So here you can't comment on maxima and minima, but actually if you see carefully, this function doesn't have either maxima or minima here at this point. Why? Because you see, as you keep on increasing positive value of x, this x cube keep on increasing. Similarly, as you keep on decreasing the value of x, if you write minus 1000, minus 2000 and all, that keep on giving you minimum to minus infinity. Okay, but at x is equal to 0, even though the differentiation is 0, the function need not have a maximum or minimum. That's why the second derivative test comes into the picture. If the function is having maxima or minimum, definitely yes, differentiation is 0. But if differentiation is 0, the function need not have maxima or minimum. This is the example. Clear? So these points are very much, very important actually, because sometimes they ask you, when you differentiate, definitely you did not have a maximum or minimum. This is the example. Okay, and if you see the graph of y is equal to x cube, it looks something like this. So 0 x, let us write this 0 other side, 0 minus x y minus y. So if you see the graph, it looks something like this. It starts like this, then it gets very flat here. It starts like this, then it gets very flat here almost, and then it rises. Okay, so anyhow, we have this tool, so let me show you more clearly. So we have this tool, so let me show you more clearly. So x cube, x to the power 3. Okay, so if you see, this is x cube graph actually. So if you see, it rises, then it goes very flat almost, and then it increases again. So at this point x is equal to 0, you can see it's not maximum value or minimum value, because the maximums and there are also minimums on the left side. Okay, so but at x is equal to 0, the derivative is 0. So this is one very important point to note actually. So if differentiation is 0, the function need not mandatorily have maxima or minima. Clear? Now let us move to the next example. I'll tell you. Here you may feel that whenever the point is point of inflection, then the function may not have maxima or minima, but actually the case is something different. Look, we can't comment. That's the reason why. If you see example, x is equal to 0 is a point of inflection, for sin x is equal to x. For sin x by x is equal to f of x. Okay, if you take this function and if you calculate the differentiation and all, definitely you will get x is equal to 0 is the point of inflection, and x equal to 0 also satisfies second derivative equal to 0. Okay, but if you see yet x is equal to 0, you can write as x tends to 0, sin x by x has a maximum value of 1. Correct? We have seen maximum value of 1 actually. Okay, look, we have also seen that Taylor says as x tends to 0, we told sin x will be almost equal to x. This is what we write as limit x tends to 0, sin x by x. If you divide this x here, this tends to 1, so this is equal to 1. This is what we write. So this has a maximum value of 1. So that's why we can never comment on it is maximum or minimum actually. Okay, it depends on the function that we generally talk about. Okay, so with this we know the procedure how to calculate this concept of maxima and minima. But now I would like to give you one important point, one very important difference between two things, which is called global maxima and minima, local maxima and minima. This is some very important point actually. Look, what is this global and local? Global maxima or minima, global maxima and local maxima. Similarly minima also, if you write global maximum and local maxima. So let us see what is this global maxima and local maxima. Look, let us suppose if you have a function like this. Okay, so this is origin, this is x, this is y, this is minus x, this is minus y. Now you see here, if you plot the graph, for example, let us suppose you got some random curve like this, and the function stopped here. Let us suppose this is the curve. Okay, this is the curve basically here. Okay, so let us suppose this is some plot of some function, some sine wave or something. There is some fluctuation meanwhile. Now tell me one thing. If I ask you what is the maximum value of this function, undoubtedly you will say this is the value, correct? So if you see within the complete interval, means from minus infinity to infinity, let us suppose this is the only part of the function. Now if you see for the complete real axis, that value which I'm writing as g1 for g, for example, this g is the maximum value globally. But let us suppose if I give you some interval that I am focusing only on this interval, for example, I am focusing only on this interval, then if you see, if I ask you what is the maximum value of this function in this interval, then definitely you will write this is the maximum value, correct? So this is local maxima within the given interval. So if interval changes, local maximum can change, but global maxima remains same for any interval. Okay, so that's the difference between global and local. You can understand by the words also. Global means totally whatever is available, the complete axis. Local means some region. Okay, so some region, if you see, this is called locally actually. Okay, I'll tell you out with the help of an example. See here, I'll ask you this question. The maximum value of x square minus 10x plus 8 in the interval 4, 6, for example. Okay, so or you can say 2, 8, let us say, is dash. Let us suppose if I ask you this question, for example. Okay, now if you apply, if you in exam such kind of questions can come, they'll give you some interval. Okay, they'll give you some region, they want you to talk on some local things. So that's why if you see, they'll give you one region. Okay, now how you will do this? Normally if you start applying the procedure of local maximum, I mean this actual global maxima and minima, let us see what comes out. F of x is x square minus 10x plus 8. So if you calculate f dash of x, this is 2x minus 10. So if you equate this to 0, x is equal to 5. So okay, let us change this question. Let us keep 3 here, for example, 3, 8, let us keep. Okay, so x is equal to 5. So if x is equal to 5, then what is f double dash of x? F double dash of x is equal to 2. Now this is greater than 0. Now tell me one thing, and you need not substitute any stationary point also. This f double dash of x is always greater than 0. Now whenever f double dash of x is greater than 0 at stationary point also, even if you put x is equal to 5, you will still get 2. So here if you see, this second derivative is actually positive. Now if second derivative is positive, from the concept of maximum and minimum, you know that the function has a minimum, but in the question they are asking you maximum. Understood? So here you will get stuck if you don't know the concept of global maxima and local maxima, or similarly global minima and local minima also. Look here, you got ended up with the second derivative being positive, but you know, if second derivative is positive, the function has a minimum, but they're asking you for the maximum value. So that's why they have given you this interval 3, 8. So what they're asking you for, look, whenever they give you some interval, you need to calculate this function at stationary point. So f of 5. So if you calculate f of 5, 25 minus 50, 25 minus 50 is minus 25, minus 25 plus 8, minus 17. So minus 17. Next, along with the stationary points, you should also calculate these points. Okay, so f of 3, if you keep f of 3, 9 minus 30, minus 21, minus 21 plus 8, minus 13. F of 8, 64 minus 80, minus 16 plus 8, minus 8. Okay, so if you see, the maximum value out of these 3 things is basically minus 8. So that's how the answer is minus 8, because it's clearly, even if you read in the form of English, you will understand this question. Maximum value in this interval is what? Okay, so if you see, this minus 8 is the maximum value in this interval, of course. Okay, and if you see carefully, out of all these values, minimum is this, which is actually because this is the point where this function has a global minimum. So even if you have this small range, doesn't matter, since this point is falling within this range at x equal to 5, the function has minimum of all the values. You take any other value between 3 and 8, you will still get some value higher than minus 17. For example, you take 4, f of 4, if you calculate f of 4, if you calculate 16 minus 40, minus 24, minus 24 plus 8, minus 16, which is actually greater than minus 17. Yes or no? So that's why if you take any value in this interval, definitely your answer will be more than minus 17, because this is actually the global minima of this function. Okay, so that's the reason whenever some interval is given, along with the value set stationary points, you should also calculate the value set the endpoints of the intervals. Okay, so that's how you need to do this. And with this we finish the concept of maxima and minima, and of course definitely we'll launch one series soon, hopefully, for solving some questions on all these things which we are covering in one shot. Okay, so this is basically some the concept of maxima and minima. So with this we conclude a differential calculus part of single variables. Okay, so we'll do integral calculus also now, and then we'll close this session basically. Okay, so let us go for the integral calculus, because calculus is a vast module, you cannot take in a single video, so we'll split it into two: single variable one video, and multiple variables means 2, 3, all others in the next video maybe. Okay, so let's talk about this once quick revision. We have talked about the concepts of limit, continuity, and differentiability. We have understood what differentiation means geometrically. Then we have talked about some applications of this differentiation, basically mean value theorems, Taylor series, maxima and minima concepts. So all these things are very much important, and I hope you got some good knowledge also in this first, you can say, almost some 3 hours of the session. Okay, so let's go for the integral calculus. So integral calculus. Integral calculus of single variable, of course. Okay, so integral calculus. So integral calculus. Now generally people feel integration a bit complex as compared to differentiation. Fact, correct? We all should agree it. Whenever questions comes from differentiation, we feel very happy that we'll be able to solve, but if questions are coming from integration, there is some kind of fear. But why this fear is existing? Because I'll tell you, actually integration and differentiation both are easy, but thing is, in differentiation, let us suppose if you don't know the derivative of any function. For example, if I given you some function and you don't know how to calculate the derivative, there is some standard procedure which is called the first principle, correct? So there is first principle of differentiation. So using first principle of differentiation, you can calculate differentiation of any function. But in integration, you do not have such principles. If I want to write integration of sin x is minus cos x plus c, definitely I should know differentiation of cos x is minus sin x. Okay, so that's why, since people don't remember these derivatives very often, they feel this integration is slightly complicated. But anyhow, you don't have any such things. You can always do the integration also simply. Look, so first let us start with fundamental theorems of integral calculus. 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 Let us see here. First theorem. Okay, fundamental theorems of integral calculus. So first, the definition of integration. Look, if capital F of x is antiderivative, means the inverse of derivative of f of x, that is continuous, that is differentiable in, that is differentiable in a comma b, or you can say open interval, but not closed, a comma b, then we write integral. This is the symbol of antiderivative, means the inverse of differentiation. Normally you see d by dx, this is differential operator, so this is inverse of this operation. So integral a to b f of x dx is equal to capital F of b minus capital F of a. This is how we define the definition of integration. Means there exists some function capital F of x such that this capital F of x is antiderivative of this small f of x. Means what's the meaning? If you differentiate this capital F of x, you'll again get small f of x. That's the meaning. Okay, for example, if you write integral cos x dx is sin x, for example, okay, you'll write this, and here this sin x is called antiderivative of this cos x. Why? If you differentiate this function, you will get this cos x again. Okay, so that's the meaning basically. And of course here it's a definite integration, you have substituted the limits also. That's the only thing. Now if this is the case, Then we'll define one very important theorem which is called mean value theorem of integration. So mean value theorem of integration. Mean value theorem of integral calculus. Mean value theorem of integral calculus. Let us see. Mean value theorem of integral calculus. Mean value theorem of integral calculus. Look, what is this mean value theorem of integral calculus? I'll write the equation, then again I'll explain it geometrically what's happening. Okay, so if f of x is continuous on a comma b, continuous on a comma b, and differentiable in open a comma b, differentiable in open interval a comma b, then there exists at least one value c, at least one value c such that c belongs to a comma b and f of c is equal to integral a to b f of x dx divided by b minus a. This is called mean value theorem of integration. Like how in differential calculus we have f dash of c is equal to f of b minus f of a by b minus a. Now this is something similar to that, integral a to b f of x dx divided by b minus a. Now let us see what is the meaning of this. Okay, now to know this you should know what is the meaning of this integral a to b f of x dx. Of course we'll take simple case that f of x is positive to explain it geometrically, but this holds good for any equation. Okay, so let us see this. Let us suppose this is your x-axis and this is your y-axis, for example. So this is 0, x, y is equal to f of x. Now if this is y is equal to f of x, now let us suppose you have some function like this, some random function y is equal to f of x. Okay, so this is y is equal to f of x, y is equal to f of x. Now let us assume this point is x is equal to a, this point is x is equal to a, and this point is x is equal to b, for example. So x is equal to a, x is equal to b. Now integral a to b f of x dx will actually give you area bounded by the curves, area bounded by the curves y is equal to f of x, y is equal to 0, means basically x-axis, x is equal to a and x is equal to b. So this means basically if you keep the shading, look, the area looks like this. Oh, something happened, just a minute. Okay, fine, sorry. So if you see the shading, this is the area basically. Now this is the area. Now what they are telling you, there exists at least one point c such that f of c into b minus a, means basically f of c is equal to this integral a to b f of x dx divided by b minus a. Now let us see what's happening here. Let us suppose if you take at least one point, there exists at least one point such that, look, let us suppose if I take a horizontal line, if this is x is equal to c, let us suppose if this is x is equal to c, this point here is x is equal to c. Now f of c will be a straight line like this, yes or no? So this, if you see something like this, this is x is equal to a, this is x is equal to b. Now let us suppose if you take this segment, if you take this segment f of c, for example, like this. Okay, so something like this. Now their intention is to tell you that there exists at least one point c such that, of course depending on the function there can be many also, but at least at one location, look, let us suppose if you form this rectangle, for example, if you form this rectangle, okay, so let us suppose you are forming this rectangle like this. If you form this rectangle, so this is x is equal to c, so definitely this value of y is nothing but f of c, you know this, okay. So if you take the area of rectangle is equal to f of c into b minus a, yes or no, correct? F of c is basically the height and b minus a is width, so this is equal to integral a to b f of x dx, yes or no? Because if you see, definitely if you keep on moving this line up and down, at least at one point there comes some location where this area which you are losing here is actually compensated here, yes or no? Here there is a blank and here it is shaded. When you are taking the area of rectangle, you are losing this area, so this lost area can be compensated in this gap here. So there exists at least one such point such that these two gets compensated each other. So that's how you have this area of the rectangle is same as shaded area part, and if you bring this b minus a to the right hand side, this is the equation that is with you, okay. So it's a simple geometrical understanding, but again it's a very powerful theorem. Why? Because mechanical students might know this. Actually, when you do something called a Rankine cycle in vapor power cycles, when you plot the TS diagram, basically if you see in boiler, it's a constant pressure heat addition, okay. So in case of boiler, it's constant pressure heat addition. So in case of constant pressure heat addition, your temperature is not constant, correct? As you keep on adding heat, your temperature keeps on increasing. So in such case, what happens, since if you want to compare it with Carnot cycles and all, what you do, you will come to some concept called mean temperature of heat addition, correct? You or sometimes you call T mean. So mean temperature of heat addition, which you assume that, you will assume the cycle that sorry, I'm talking some mechanical things, but yeah, so if some of you are there, you can connect to it. So if you see, this mean temperature of heat addition is that temperature at which if you supply the same amount of heat at that temperature, your efficiency of the cycle remains same, work output remains same, okay. So that mean temperature of heat addition is actually calculated using this equation. T mean is equal to the heat supplied by change in entropy at that place. So TDS, integral TDS gives you the heat interaction between state 2 to 3 boiler states, and delta S, which means S3 minus S2. So this equation is something similar to this, okay. So both these are same actually. So mean temperature of heat addition is actually calculated using this mean value theorem of integration, okay. So now let us go for some other part. Newton-Leibniz rule, one very important rule again. So Newton-Leibniz rule actually, okay. So let us see what is this Newton's Leibniz rule, okay. So let us see this Newton's Leibniz rule. This is basically differentiation of integration, okay. So if phi of x comma psi of x are two differentiable functions, are two differentiable functions, and f of x is continuously differentiable. F of x is continuously differentiable. What's the meaning of that? You can integrate this f of x very easily. Differentiable. Then d by dx of integral phi of x to psi of x f of x dx means basically you have variable limits and you are differentiating this, okay. So this is actually equal to f of psi of x, means you see, you might have studied about composite functions, correct? Means for example, if I say f of x is equal to x square, g of x is equal to sin x, for example, then if I write g of f of x, for example, let us suppose if I write like this, then what happens? This is g of x square, so g of x is sin x, so g of x square is sin x square. This is how you work out the composite functions actually. So f of psi of x into psi dash of x minus f of phi of x into phi dash of x, okay. So this is called Newton's Leibniz rule, and this is very important rule actually, because many times, especially if you are writing XC and all, there are many questions on this Newton's Leibniz rule, okay. So, and if you notice Newton's Leibniz rule, some nice questions in integration can be solved easily, okay. We'll see when we solve the PYQ series or something, okay. I'm continuously checking because I'm doubting my battery is going off or what, okay. So yeah, we have enough battery, good. So d by dx of this thing is basically equal to this variation. Now, so basically these are some fundamental theorems and rules of this integral calculus. Now one I'll give you some standard integrals which could be helpful to you. So some standard integrals, okay, like how I have given you some standard derivatives. Let us now work the reverse of that. So some standard integrals. Okay, so first integral x power n dx, this is equal to x to the power n plus 1 divided by n plus 1 plus some arbitrary constant. C is some arbitrary constant, means whatever the value you put in place of C, still this equation holds good. Okay, if you differentiate the right hand side by taking any value of the constant, you will get x power n. That's the meaning. Okay, and this is valid when n is not equal to minus 1, of course. Okay, if n equal to minus 1, division with 0 not defined. Okay, so what is the case with n is equal to minus 1? Means 1 by x dx, this is log mod x to the base e plus constant. Okay, next 3, sin x, integration of sin x dx is again minus cos x plus constant. Similarly, integral cos x dx is equal to sin x plus constant. 5, integral secant square x is equal to tan x plus c, because you know tan x differentiation is secant square x. So anyhow, let us write integral tan x dx is equal to minus log mod integral tan x integral tan x dx is minus log mod secant x. Okay, so minus log mod cos x, actually you can write minus log mod. Anyhow, let us see, before going for tan x, let us write one result. Integral f dash of x by f of x dx is equal to log mod f of x to the base e plus constant. Okay, why this is the case? Because if you differentiate this, you will again get this 1 by differentiation of this function is 1 by, if you write differentiation of log mod f of x to the base e, if you write this, this is 1 by mod f of x into differentiation of mod f of x is mod f of x by f of x, derivative of mod x is mod x by x. So that's how this is mod f of x by f of x into the inner derivative of f of x is f dash of x. So these two terms get cancelled out, so you have f dash of x by f of x. That's how this integration is that basically. Now if you write for tan x, integral tan x dx, this is equal to integral cos x, sorry, sin x by cos x dx. So if you adjust a minus sign here and there, so minus sin x is nothing but derivative of cos x. So this is minus log mod cos x to the base e plus constant. Okay, so if you if you take a minus, if you take this minus sign to the power 1 here, cos x inverse, so 1 by cos x is nothing but secant x. So this can be written as log mod secant x to the base e plus constant. Anyhow, okay, so that's also same case. Now let us see 8th one, integral cot x dx. So this time, you know, this is cos x by sin x dx, which is differentiation of sin is directly cos, so log mod sin x to the base e plus constant. If you want to play with a minus, you can write minus log mod cosecant x to the base e plus constant. Okay, so minus log mod cosecant x plus constant. Similarly, if you write for secant x, integral secant x dx, so this is log mod secant x plus tan x to the base e plus constant. Of course, e I have written natural logarithm, so 10th integral cosecant x dx, this is equal to minus log mod cosecant x minus cot x plus c, actually here. Okay, will there be a minus sign here? Let us check here. So integral cosecant x, if you take integral cosecant x, if you take here dx, so what we can do, we can rationalize with this. So cosecant x times cosecant x minus cot x by cosecant x minus cot x. If you write this by cosecant x minus cot x dx. Okay, so if you see, this is cosecant square x, so cosecant square x is differentiation of minus cot x, because cot x is minus cosecant square x. So if you have cosecant square x, this is minus cot x, and cosecant x is minus cosecant x cot x. Okay, so that's how it's finished. So log mod cosecant x minus cot x, no minus sign, cot x plus constant. That's how we have this formulas. Okay, and if you write for some more like sine inverse and all, I'll tell you after one principle actually, which is called highlight principle and all. I'll tell you how to write for inverse functions. So right now we will put inverse functions on hold. Now let us see 11th, integral a power x dx. This is a power x by log a to the base e plus constant. Okay, and 12th, integral e power x. So you know, if you put a is equal to e, this denominator turns 1, so e power x plus constant. Okay, so 13th, integration log x also. Again I'll okay fine, integration log x I can give you, it's a small one. Log x dx is x into ln x minus x plus constant. Okay, so basically x times of log x minus 1 is what you will have generally. Okay, so x into log x minus x. So 14th, integral f dash of x by root f of x is equal to 2 times of root f of x plus constant. So sometimes if you have sin x by root cos x or cos x by root sin x, such kind of things, you can play with this. Okay, so 14th. So 15th, inverse of algebraic functions is done. Logarithmic we have seen, then exponential we have seen, trigonometric we have seen. So inverse functions we will see later. Okay, so basically these are the functions, and I would like to give one more also. 15th, integral f of x into f dash of x. So sometimes you have sin x into cos x, these kind of things. So the answer is half into f of x whole square plus constant. Why? Because if you differentiate this, you will get the same thing again. Okay, so normally you need not remember these formulas in a single go, but as you keep on using them, you will get familiar with them. Okay, so now this is 15th and 16th. So basically, yeah, these are the more or less the general formulas that we have. Okay, now if you do for some things, some algebraic functions, which I'm not, okay fine, let us talk about that later. Okay, or now itself, but okay fine. So let us see, integral root of a square minus x square dx. So this is one very important integral actually, because we calculate the area of ellipse, all these things using this integration. Okay, so anyhow, so right now I'm giving you the formula is x by 2 into root of a square minus x square plus a square by 2 into sine inverse of x by a plus constant. Okay, it's not a very complicated integral, it's actually very easy. If you take x is equal to a sin theta or a cos theta, and if you do substitutions and calculate the things, you will get that result very easily. Okay, so I'm not deriving it because it's a fast series before GATE 2023, it's like some revision kind of thing. So that's why we are giving x by 2 into root of a square minus x square, all these formulas directly. Okay, now if you talk about integral 1 by a square plus x square dx, this is 1 by a times of tan inverse x by a plus constant. Okay, so next integral 1 by root of x square minus a square dx. So this is sine inverse x by a plus constant. Okay, so root of 1 minus a square minus x square, sorry, if you differentiate this, 1 by root of 1 minus this try into 1 by a, so root of a square minus x square. Yes, so basically if you see, signs we have altered here, so this is a square minus x square. If there is minus 1, then it's cos inverse actually. Okay, so integral root of 1 by root of a square minus x square, all these things, it's you can calculate them, but here this is the some important result that comes out here. Okay, now how to integrate two functions, product of two functions. If you have product of two functions, how to integrate them? Okay, so let us see integration by parts. Integration by parts. So if you have two functions, how to integrate them actually? So let us see here. If you have this two parts, for example, means if you have this integral f of x into g of x dx. So if you have this function, how you will integrate? This is actually equal to f of x into integral g of x dx minus integral f dash of x into integral g of x dx to this whole dx plus some constant. Okay, so this is how you integrate the product of two functions actually. Okay, so first function into integration of second function minus integral of differentiation of this first function into this second integral dx plus constant. Okay, now when you apply this integration by parts, you can, of course, you can multiply, you can keep the product in any way, you will get the answer. But generally there's one principle which if you follow, you will get in a sequence, in a systemized way. Otherwise what happens, sometimes calculations go out of range, means they go very big actually. Okay, so when you are deciding the product, actually this product of the functions, product of f of x into g of x, product of f of x into g of x is denoted by, or is decided by 𝐂𝐸𝐬𝐿ate order. There is one order which is called this 𝐂𝐸𝐬𝐿ate. And what does this 𝐂𝐸𝐬𝐿ate mean? I for inverse functions, L for logarithmic functions, A for algebraic, T for trigonometric, and D for exponential functions. Okay, so I'll give a quick note. Inverse, then log, then algebraic means all these functions, trigonometric and exponential functions, like this, exponential functions. Okay, so we have this many things like this. So integration by parts is what we generally do. And of course using this, let us suppose if I want to, because I want to give you one technique also here. Okay, so see, let us suppose if I calculate integral x cube into e power x dx, simple case. Okay, x cube into e power x dx, for example. Okay, now let us see what or how it happens. Okay, so first function into integration of second function minus integral of differentiation of this first function 3x square into integration of second function, which is again e power x dx. So x cube into e power x minus 3 times of, now integral x square into e power x, so again first function into integration of second function minus integral derivative of this first function, which is 2x into integration of that. So plus, so basically this is what you have. Okay, so if you simplify this, x cube e power x minus 3x square e power x, so minus of minus plus, and 2 if you pull out, 6 times of integral x into e power x dx is what you have. So x cube e power x minus 3x square e power x plus 6 into this integration. If you simplify this, first function into integration of second function is this, minus integral differentiation of this first function is 1, integration of e power x is e power x dx. This is what you have. So if you write the final result, you have x cube e power x minus 3x square e power x plus 6x e power x minus 6 times of e power x plus constant. Now if you are deleting the integration, so this is how you apply by parts. Now in by parting, why I have taken the first function as x cube, because if you follow the 𝐂𝐸𝐬𝐿ate order, a comes before e, correct? So algebraic functions must be taken before exponential functions, so that's why I have taken x cube here. Okay, so x cube is taken as the first function and I have done the integration. But if you, okay, I have got some 4-5 steps and I have got the answer. But if you see, there is one technique in integrations, that integral uv, let us suppose if we have product of two functions, integral u into v, let us suppose if we have this, we get this as u into v1. v1 is integration, first integral of v, okay, minus u dash into v2 plus u double dash into v3 minus u triple dash into v4 plus, and so on, like this. Okay, this goes on actually. Now what happens, whenever this u first function is algebraic function of some finite degree, then what happens, after certain terms the differentiation term becomes 0. For example, if you differentiate a third degree function 4 times, then what happens, differentiation is 0 for that, correct? Similarly, if you differentiate a quadratic function 3 times, then derivative becomes 0. So whenever one of the functions is actually algebraic function having certain finite power, then definitely this differentiation will come to 0 after some time, so you can simplify the result easily. For example, in this case, if you see integral x cube into e power x dx, so if you take first function x cube into, what is integration of this e power x, okay, minus derivative of this x cube 3x square into what is the integration of this function, e power x function, again e power x, plus derivative, second derivative of this function. So this 3x square is the first derivative. So what is the differentiation of this 3x square? 6x, into integration of this e power x, again e power x, minus differentiation of this 6x, 6, into integration of this e power x, plus differentiation of this 6, 0. That's it. From here it is finished. So we'll round off to a constant. And if you see, this result and this result both are same actually. Okay, but this technique is generally helpful only when one of the functions is algebraic, or you can say first function is algebraic function with some finite degree actually. Okay, let us suppose if in place of x cube, if I have some sin x or cos x, for example sin x into e power x or cos x into e power x is there, then what happens? Sin x cos x minus sin x minus cos x, again sin x. This loop keep on repeating. I'll never come to a conclusion. Okay, I'll never can truncate my series. But when one of the functions is algebraic, you can definitely go for this technique actually. Clear? Next. So similarly, if you write this function x square into sin x, if you write this sin x dx, so first function into integration of sin x, integration of sin x is minus cos x. Correct? Integration of sin x is minus cos x. Okay, now minus derivative of x square 2x into integration of minus cos x. What is the integration of minus cos x? Minus sin x. So minus sin x, because if you differentiate minus sin x, then you'll get minus cos x, plus differentiation of 2x, 2, into integration of minus sin x cos x, plus minus differentiation of 2, 0. So we'll write some arbitrary constant here. The series got ended up. So this is how you actually do the UV integration depending upon the things like this. Okay, now so with this we generally close this. Okay, before closing I would like to give one result which is for sin inverse x, because I've promised you that I'll give. So see here, integral sin inverse x dx, integral sin inverse x dx. So what we'll do, integral sin inverse x into 1 dx. Let us write this. Okay, so this is again sin inverse x. So Euclid principle, inverse, this is already in the first place. So integration of this is sin inverse x into integration of this 1 is x, minus integral derivative of sin inverse x 1 by root of 1 minus x square into integration of this 1 is x dx. Okay, so this is what you have. Basically you applied this by parts, integration by parts. Okay, so if you calculate this, then this integration is equal to x into sin inverse x. Next, if you see the differentiation of 1 minus x square, this is minus 2x. So what we can do, we'll multiply a minus inside and outside. We'll write 1 by 2 and a 2 here. Okay, if you multiply, then you can see x into sin inverse x plus half into, this is integration of minus 2x by root of 1 minus x square. So if 1 minus x square is your function, this minus 2x is like f dash of x. So this is 2 times of root f of x. So 2 gets cancelled. So basically integral sin inverse x dx, integral sin inverse x dx is equal to x into sin inverse x plus root of 1 minus x square plus constant. Okay, so this is how you can calculate integration of sin inverse x. Similarly log also, you can take log as one function and 1 as second function, and you can do the integration in by parts. Okay, then you'll get x into log x minus x. Okay, so all these things are very simple things. So this is what you have with this you say indefinite integrals. Okay, so now let us see some properties of definite integration. Okay, so properties of definite integration, which is one important part actually. So see, properties of definite integration means basically summing up properties of definite integrals. Properties of definite integrals. Okay, so see here, properties of definite integrals. So first property, integral a to b f of x dx, this is equal to minus integral b to a f of x dx. Why? Because we have defined this integration as capital F of b minus capital F of a, if you remember, correct? So let us suppose if I change the integrations, then that becomes capital F of a minus capital F of b. There is some minus sign difference between these two, so that's why a minus sign is kept here. Second, integral a to b f of x dx is equal to integral a to b f of a plus b minus x dx. Of course, in all these examples I'm assuming f of x is differentiable at a waypoint. Okay, so that's why I'm taking directly. So if f of x is differentiable, only then I can write this, because if it's not differentiable, then derivative doesn't exist, you cannot integrate them basically. Okay, so this is how we can write. Okay, and how this is coming, it's very simple. If you see some 1-2 steps, you can write. Look, let us take this integral. Okay, so because some of you might be interested how this comes. So let a plus b minus x is equal to t. Then what happens if you differentiate this? Differentiation of a 0 plus differentiation of b 0 minus dx is equal to dt. So dx can be replaced with minus dt. What about lower limit? Lower limit x is equal to a, correct? So this implies a plus b minus x is equal to t. So if you replace x is equal to a plus b minus a is equal to t. So a gets cancelled. So t is equal to b. T is equal to b. Next, upper limit. If you calculate upper limit, what comes here? A plus b minus x is equal to t, and in case of upper limit in terms of x is equal to b. So this implies a plus b minus b is equal to t. So t is equal to a. So by making the substitution, a plus b minus x is equal to t, your dx is minus dt, lower limit is b, upper limit is a. So if you substitute all these 4 things in this integration, integral lower limit became small b to a f of t into dx is nothing but minus dt. So if you using this minus sign, if you change this limits, this becomes integral a to b f of t dt. Okay, so this is how you have the things. So this is same as integral a to b f of x dx. Whatever could be the variable, the result remains same. So that's how these 2 integrals are actually the same value, and this is actually one very important property of definite integration. You will be able to solve some good integrals using these things. Okay, so integral a to b f of x dx, all these things. Okay, so right now I'm not looking into the problems. This is a quick go of some revision for the theory. So that's why you are seeing a lot of theory, but later when it comes to practice, definitely in practice series I will bring the practice series also, so very soon, and definitely we will try to solve some good questions in mathematics. Okay, and that will make you more confident even. Okay, so let us look at these properties quickly. Third, if C is a point in a comma b such that f of x is not differentiable, f of x is not differentiable, then integral a to b f of x dx, this is equal to integral a to c f of x dx plus integral c to b f of x dx. Okay, so basically you need to split the integration at that point whenever they are not differentiable. Okay, means let us suppose, for example, if I'm talking about integral minus 2 to 2 mod x dx, then you need to split the integration at 0, because definitely mod x is not differentiable at x equal to 0. So you need to split that into 2 integrals, minus 2 to 0 and 0 to 2. Okay, so that's how you need to do the things. Then fourth, if, okay, let us write this. Integral 0 to 2a f of x dx is equal to 2 times integral 0 to a f of x dx if f of 2a minus x is equal to f of x. Okay, so sometimes they give you functions like sine and all, and they keep 2 pi things like this here. So this can be split in this form, 2 times of integral 0 to a f of x dx actually. Okay, so if you can write this. Now fifth, integral minus a to a f of x dx is equal to 2 times of integral 0 to a f of x dx if f of minus x is equal to f of x, means if this is even function. Similarly, this is 0 if f of minus x is equal to minus f of x, means if this is odd function, then this result is basically 0 directly. Okay, so this result is also again useful at many places. Whenever you have some even functions, then this minus a to a can be written as 2 times of this integration actually here. Okay, so that's again one important thing. Next, we'll go for one more property. Integral 0 to pi by 2 sine power mx dx. This result is same as integral 0 to pi by 2 cos power mx dx. Okay, so cos power mx dx, and this is equal to basically, if you see, if you write this equation, m minus 1 into m minus 2 into m minus 3 into, and so on. Basically this goes on, and finally you will end with either 2 by 3 or 1 by 2, depending upon m is even or odd. Okay, so if m is even, you will end up the series with 1 by 2. If m is odd, you will come by 2 by 3 into k. So what is the value of k? Where k equal to pi by 2 if m is even, k equal to pi by 2 if m is even, and k equal to 1 if m is odd. Why this is coming and all, we'll see when we go for this gamma function, all these things. Okay, so k equal to pi by 2 if m is even, and k equal to 1 if m is odd, and it depends upon this m being even or odd. Okay, so one last property I would like to give you here, which is a bit important. So integral 0 to pi by 2 sine power mx into cos power nx dx. So this is equal to, if you see, we will have this result. So see here carefully, this is m plus n into m plus n minus 2 into m plus n minus 4 into, and so on, 2 or 1. Now this is in the denominator, means basically once you know this m and n values, then you can write m plus 1, then every alternative number till 1 or 2 depending upon the things. Now here m minus 1 into m minus 3 into, and so on, 2 or 1 again here, into n minus 1, n minus 3, and so on, 2 or 1, this whole value into k, into k. So where k is equal to pi by 2 if both m and n are even, if both m and n are even. Similarly, if you see, k is equal to 1 otherwise. What is the meaning of otherwise? If m is even, n is odd, or if m is odd and n is even, or if both are odd, in those cases your k value is equal to 1. Okay, but these are very simple things to remember. Here if you see, m will, if there is m, you'll start with m, then m minus 1, m minus 2, m minus 3, this multiplication you keep on going, and depending upon m being even or odd, you'll substitute pi by 2 or 1 respectively. Similarly in this case also, if you see, if you identify what is m and n, then these values, writing this expression is also very simple actually. Okay, I'll give you one example which is some common thing. So if you see, for example, I'll give you one simple thing, 0 to pi by 2 sine square x dx, for example. Okay, sine square is very simple, so let us take sine power 4x. Okay, sine power 4x dx, for example. Okay, so sine power 4x. Okay, sine square will take, simply let us keep the thing simple, let's not make complicated, sine square x dx, for example. So this can be written as, if you want to integrate this, 0 to pi by 2, 1 minus cos x cos 2x divided by 2 dx. Okay, so this is what you will get. So 1 minus cos 2x is basically sine square x. So if you integrate this, 1 by 2 times of integration of 1 is x minus integration of cos 2x is sine 2x divided by 2. So within the limits 0 to pi by 2. So if you simplify this result, 1 by 2 times of, when you substitute x, pi by 2 minus, when you substitute x is equal to pi by 2 here, this is sine pi, 0. So when you substitute 0, both are zeros. So this is pi by 4. This is the result which you have, which is pi by 4 actually here. Okay, so half into 1 minus cos 2x. So integration of cos 2x is sine 2x, and it is 2. Fine. So if you substitute from 0 to pi by 2, you have this pi by 4. Good. Now if you see, if you calculate this result using this analysis, so m value is 2 actually. So this integral 0 to pi by 2 sine square x dx is equal to So look, you have 2 here, so m is 2, so obviously 1, that's it, no more numbers is into k. So here n is even, so k value is pi by 2, that's it. So this is pi by 4 directly, so this is pi by 4 and this result is also pi by 4 actually. Clear? So that's how you can apply this rule for calculating some powers of sine and cos combinations. Okay, and also I'd like to give one more example here. Integral 0 to pi by 2 sine square x into cos square x dx. So let us suppose you have this integration, for example. Okay, now if you have this integration, how will you proceed? Basically you can write, there are multiple ways of doing this actually. Okay, but if you simply apply this rule, you can see this m plus n is 4, so 2, that's it, into 0 you cannot write, this is 2, so m minus 1 is 1, that's it. Here also m minus 1 is 1. Now both are even, so k value is pi by 2. So if you simplify, pi by 16 is the correct answer for that integral. Okay, so pi by 16 is what you will get if you solve that integration. Clear? So m plus n value, then after two different, means basically every alternate numbers you need to write. Since m is 1, m is 2, m minus 1 is 1, and you don't have any series to continue, so 1 is the cases for both this, and you have the cases. Okay, now why this integrations is very much important for you? Okay, integration means basically adding up, summing up, and you have a lot of applications. For example, if you see geometrical applications, you can find the area between the curves. Okay, so how we will find the area between the curves? See here, so let us write area between curves, area between the curves, area between the curves. So how you'll calculate this area between the curves? Basically in a very normal way, that if f of x comma g of x are continuous and differentiable functions, continuous and differentiable functions, continuous and differentiable functions in a comma b, and let f of x greater than f of g of x. For example, say let us suppose if f of x is greater than g of x. So in that case, if f of x is greater than g of x, then the area bounded between y equal to f of x and y equal to g of x and y is equal to g of x between x is equal to a and x is equal to b is given by, so if you see these two areas, this is given by this result, a is equal to integral a to b. Since f of x is more, you can write f of x minus g of x dx. So this is the integration. So if f of x and g of x are given to you, then this f of x minus g of x will be some function of x, and you can integrate that. And how you will do this? Basically like this. Look, if you have some functions like this, then let us suppose this is y is equal to f of x, y is equal to f of x. Okay, and if you see, let us suppose this is y is equal to g of x, y is equal to g of x. Okay, now if you take this area x is equal to a, this is x is equal to a, and let us suppose this is x is equal to b, x is equal to a, x is equal to b, this is x axis, origin y. Now the area here is this shaded part. So how do you know this area is given by this equation? Because if you calculate integral a to b f of x dx, you will get the total area which is even below this orange curve, correct? And if you calculate integral a to b g of x dx, you will get this area below the orange curve. So if you take the difference to get this area, this total area minus this area which is below the orange will actually give you the area which is bounded. So that is actually f of x minus g of x. But one very important caution here is this f of x should be definitely more than this g of x function. Okay, otherwise your result goes wrong actually. So your f of x function should be definitely more than your g of x function. Okay, so this is one very important thing. Because why this is important, I will give you the help of an example. If I ask you to calculate, find the area between the curves y is equal to sin x, y equal to 0 between x equal to 0 and x is equal to 2 pi. Let us suppose if I write this, okay, let us suppose if I write this, then if you plot these curves, means basically if I give you this sin x minus 0, you generally feel that sin x is more. So if you do this integration 0 to 2 pi sin x minus 0, which means sin x dx, you will end up with 0. Correct? This answer is 0 because the integration is minus cos x, cos 2 pi and cos 0, both are same, so the answer is 0. But actually speaking, there is some area which is bounded between sin x and 0 actually. That you will come to know if you draw the graphs. That's the reason why I've given you graphs in the beginning. So let us try to draw now. So if you see, if you try to draw the graph, this is, you know, x-axis, this is x-axis, then this is your y-axis, origin, x, y. So sin x, so if you take the graph of sin x like this, something for example, and let us suppose this value is 2 pi and this value is pi. Now the area bounded is actually this complete area. This complete area, correct, is the area bounded. But why you are getting 0 answer? Because you have committed one mistake, that from 0 to pi sin x is on the top and x-axis is on bottom, so sin x minus 0 is good. But sorry, excuse me, so but from pi to 2 pi, if you see sin x is on the bottom and x equal to, I mean this y-axis, sorry, y equal to 0, means basically this x-axis is on the top. So if you want to calculate this area, I told you first f of x should be always above g of x. So if you want this area, you should do integral 0 to pi sin x minus 0, because sin x is on the top, plus pi to 2 pi, you know, 0 minus sin x, because x equal to, means x-axis is on the top. So that's why this is the integration you need to do, because after x is equal to pi or at x equal to pi, the curves are intersecting and the curve which is on the top till then is going bottom. Okay, so that's why you need to split the curves at any point where they actually cut each other. You need to check carefully and you need to do this integration. So if you do this integration now, minus cos x 0 to pi plus integration of minus sin x is cos x from pi to 2 pi. So if you substitute, minus cos pi is minus 1 minus cos 0 is 1 plus cos 2 pi is 1 minus cos pi is minus 1. So total value is 4 actually. Okay, so basically you have seen, if you take only till this part integral 0 to pi by 2 sin x, this value is actually 1. Okay, this value is actually 1. So that's why this total area is 4 times of this part. So that's why 4 times of 1 is 4 is what you will get actually here. Okay, so this is how you get this equation. Similarly, if you are calculating length of a curve, let us suppose if you have some length of the curve, if you have a curve which is of some not proper geometry. Okay, let us suppose if I give you a line segment and if I ask you what is the length, you can easily tell me, like you will put a scale and you will tell me. Okay, so but let us suppose if I give you some random curve like this, length of a curve. If you see, let us suppose if I give you some random curve like this, no, this is straight line, so some random curve y is equal to f of x. So what is the length of this curve? From to, let us suppose if I establish a coordinate system, so if you see, I have established some coordinate system. So this is origin x, y. So let us suppose this is x is equal to a, this is x is equal to a, and this is x is equal to b. Now my aim, so this is x is equal to a and this is x is equal to b. Now my job is to calculate the length of the curve from this point to this point, let us say. Okay, mathematically, of course. Physically, if you want to measure, how do you measure? You take a thread, keep the thread along this curve, then take the thread, make it straight, put it on a scale, you will get the length. Okay, but mathematically, how do you calculate this? Look, and the equation of the curve is given, but it's not a very regular geometry. So in such cases, how you do? How you do is like this way. So look, what we'll do is we'll take some small length ds. Okay, so we'll take some small length ds, and this small length ds, which is like this, you project it onto this coordinate system. So this is dy and this is dx. So whenever ds is very small, you can make sure, we can assume that this curve is actually a straight line. Okay, when these points are very close, you can see the line and the curve almost they look same. So ds square will be equal to dx whole square plus dy whole square. Pythagoras theorem. If you apply Pythagoras theorem for the right angle triangle, you will get this ds whole square is equal to dx square plus dy square. Okay. Now, if you see, ds is equal to square root of dx whole square plus dy whole square. So here, if you take this dx whole square out, you will get the result like this. ds is equal to root of 1 plus dy by dx whole square into dx, actually like this. Okay, so root of 1 plus dy by dx whole square dx. So this is the length of the small element. So if you want the total length, here dx is the integrating variable, so you need to integrate from a to b. Say therefore total length of the curve, total length of curve between x is equal to a and x is equal to b is integral a to b root of 1 plus dy by dx whole square into dx. Okay, so this is what you'll have, root of 1 plus dy by dx whole square into dx. So it's a simple Pythagoras theorem. Some 2-3 steps if you apply, you will get that. Okay, so and once if they give you the variation of y with respect to x, you will get dy by dx. So you can solve this integral, okay, to get the length of the curve actually. Okay, now let us try to understand one thing. Areas, or you can say surface areas and volumes of the solids generated. Surface area and volume of the solid generated. You can again calculate this using some simple integration techniques. Surface area and volume of the solid generated. Look, why you will get a solid. Look, let us suppose if you draw a line, for example. Now let us suppose you have some random curve, for example, some random curve y is equal to f of x. This curve equation is y is equal to f of x. Now let us suppose if you are revolving this curve about this axis, then definitely you will get a solid, correct? Depending on this curve, you will get some solid. If it's a straight line, you will get some first term of a cone. If it's a horizontal line, you will get a cylinder. Depending on this curve, you will get some different solid. Now once that solid gets generated, the solid will have certain volume and also the solid will have certain surface area. So how do we calculate that? Look, so again, if you assume this as your y-axis, origin x, y. Now if you evolve this, it comes out something like this. So this is how you will get a solid, correct? Now what is the surface area of this solid? Look, let us suppose if you take a small section ds, small length ds here, then definitely if you see, this is how we have the curve, correct? I am highlighting this with some different color so you can see. So this is small disk that you will get by evolving the small element of length ds. Now if you want the surface area, then you can see surface area is basically this, correct? This is the surface area of the small disk. So what could be the surface area? Let us suppose at this location the height from this base is y. So surface area of that ds is equal to surface area dA, basically small surface area, is equal to this circumference into this thickness ds gives that. Okay, so 2 pi y into ds, correct? So 2 pi y into ds gives the surface area because it's like a disk, for example. Okay, so if you take, for example, this is like a small disk that is coming here. So basically if you want the surface area of this small disk, you need to multiply this circumference, means basically this perimeter you need to multiply with this thickness ds, then you will get the surface area of this disk. Okay, so this is how you will get the surface area of this disk. So 2 pi y into ds. So this implies total surface area total surface area is equal to, between x is equal to a to x equal to b, if you take, let us suppose, if this coordinate you have taken, if this coordinate you have taken x is equal to a, and if this coordinate you have taken x is equal to b, means basically the curve in between x is equal to a and x is equal to b, then this integration is integral a to b 2 pi y ds. Okay, so this implies total surface area A is equal to integral a to b 2 pi y into ds, and ds is nothing but out of 1 plus dy by dx whole square into dx. Okay, so this is how you will get the surface area of any solid. Surface area of any solid. Okay, now what about the volume? The same diagram, if you see, volume, small elemental volume dV is equal to, from this diagram, if you want to calculate the volume of the disk, instead of perimeter you need to calculate the cross sectional area, correct? So basically in that case, this is the cross sectional area of the disk. That cross sectional area has to be multiplied with the thickness. So what is the cross sectional area? Circle pi y square into ds. So this implies total volume V. Total volume V is equal to integral a to b pi y square. So pi times of y square into ds basically here. Okay, so ds is out of 1 plus dy by dx whole square into dx. And generally sometimes what you do, this dy by dx values will be very small when the curves are very flat or with very little inclination. This dy by dx will be very small, so dy by dx whole square will be much smaller. So in such cases you approximate this as integral a to b pi y square dx. Okay, so this is what you have for the expression to calculate volume, and this is the expression to calculate the surface areas. Okay, so this is how you calculate surface areas of solids, and also volumes of the solids actually. Clear? Now we have one last part, which is the gamma functions and the beta functions. Of course, something which is important at this level. So if you see gamma functions, basically gamma function. So this gamma function, basically, if you see this gamma function, so the integral 0 to infinity e power minus x into x power n minus 1 dx is said as gamma function of n, gamma function of n, gamma function of n in x, because it's in terms of x actually. Okay, so that's why it's called gamma function of n. It is denoted by gamma n. Okay, so gamma n is equal to integral 0 to infinity e power minus x into x to the power n minus 1 dx. Okay, and if you see few properties of this gamma function, properties of gamma function. Properties of gamma function. Then if you say this properties of gamma function, first, if n is integer, gamma of n plus 1 is nothing but n factorial, and of course factorials are defined only for positive integers. So definitely you can see gamma, if n is a positive integer, gamma of n plus 1 is equal to n factorial, and you can write this gamma of n plus 1 as n times of gamma n actually. Okay, so basically n factorial can be written as n into n minus 1 factorial, and that n minus 1 factorial can be written as gamma n actually. Okay, so gamma of n plus 1 is equal to n times of gamma n. Third important property, which of course it's very not simple to prove, but you can take the result, gamma of 1 by 2 is equal to square root of pi actually. Okay, so this, it is very small to see, but actually if you want to calculate this, if I want to show you this result, I should consider this thing, integral 0 to infinity e power minus x square plus y square dx dy. This is the integration which I need to do to tell you or to prove you that how gamma of 1 by 2 is equal to root pi. That is a multiple integral, and that too not very simple integral. So that's why we'll see that in the next lecture, that when we talk about multi-variable calculus. Okay, so anyhow, right now this is not the importance, but, and also fourth property that I would like to give you, gamma of minus 1 by 2 is equal to minus 2 times of square root pi. Okay, so all these are 4 properties, are very important properties for this gamma function. So gamma of minus 1 by 2 is minus 2 times of square root of pi. If you can assume this, I can show that very easily, because if you see, gamma of n plus 1 is n into gamma n, correct? This is what you have. So if you put n is equal to minus 1 by 2, minus 1 by 2 plus 1 by 2 is equal to minus 1 by 2 into gamma of minus 1 by 2. So this implies gamma of minus 1 by 2 is equal to minus 2 times gamma of 1 by 2 is root pi. That's how I can show you this result very easily if you can accept this. Okay, so these are the general for general important properties of gamma function. So sometimes they give you values like this and they'll ask you. Okay, so look, I'll give example of one gamma value. So let us suppose if they ask you what is gamma of 7 by 2, for example. Anyhow, if they are integers you will solve, but let us suppose if they give you gamma of 7 by 2, for example, how to go for this? Okay, so gamma of 7 by 2 is equal to gamma of 5 by 2 plus 1. You can write this. So this is n plus 1, so n into gamma n. So this can be written as 5 by 2 into gamma of 3 by 2 plus 1. So this is 5 by 2 into 3 by 2 times gamma 3 by 2. So this is equal to 5 by 2 times of 3 by 2 into gamma of 1 by 2 plus 1. So this can be written as 5 by 2 times 3 by 2 into 1 by 2 times gamma 1 by 2. So this gamma 1 by 2 is square root of pi. So 15 by 8 into square root of pi. This is how you calculate gamma of 7 by 2 value with this succession. Okay, and one last thing before we close this lecture is beta functions. Okay, so this beta functions is also again certain important thing. So beta function actually. So if you see the integral beta function means basically beta function is also integral. The integral integral 0 to 1 x power m minus 1 into 1 minus x whole power n minus 1 dx is said to be beta function of m comma n in x actually. Okay, and it is denoted by beta of m comma n. Okay, so it is denoted by beta of m comma n, and beta of m comma n is equal to gamma times m into gamma times n divided by gamma of m plus n actually here. Okay, so this is how the beta functions are calculated basically. So whenever I give you certain integrals, integral 0 to 1 x power 5 into 1 minus x whole power 6 dx, when you assume 1 minus x is equal to t, again x gets converted to 1 plus t whole power 5, then things are not very easy, but using this gamma function you can easily sort out the things. Okay, so this is about the the beta function, and this beta function has also got some properties, properties of beta function. So if you take this properties of beta function, so properties of beta function, if you take, we will get like this. First function, beta of m comma n is same as beta of n comma m. Okay, so means basically if you replace this m and n values, still the result remains the same. You can check it out by putting 1 minus x is equal to t and changing the limits of integration. You will again get same beta of m comma n. Okay, and second property is beta of m comma n can be written as integral 0 to infinity x power m minus 1 divided by 1 plus x whole power m plus n dx, which is of course same as integral 0 to infinity x power n minus 1 divided by 1 plus x whole power m plus n dx. Okay, so these are again some very good properties that could by putting x is equal to 1 plus x is equal to t and all these substitutions, you can generate those results. Okay, and one last property that I would like to give here is integral 0 to pi by 2 sine power p theta into cos power q theta d theta. This is equal to half times of beta p plus 1 by 2 comma q plus 1 by 2 actually. Okay, so this is one result again, which is basically that's holding good for this limits 0 to pi by 2 sine power p theta into cos power q theta. So all these properties are basically some good properties of beta function and gamma functions, with which you will be able to solve the integrals slightly easier. Okay, so with this, almost some 71 pages of notes I think we got, some hectic notes, but yeah, basically these are some good properties of this definite integrals and all these things. Okay, so with this we conclude this video on basic calculus of single variable. Okay, and basic calculus of multi variables we'll look in the next video, because calculus is a very vast subject which cannot be to be honest, we cannot deal it in one single video or like that, so we'll split that. So in this video we talked about single variable calculus, and this is basic calculus. Most of the things you will be seeing in +1 +2 level and diploma level, but the next things, basic calculus of multi variables, or you can see differential equations, vector calculus, all these things, they have certain great impact of engineering applications. Okay, so we'll see all those things later. And finally I have one slide for you also, I kept it here, yeah, this slide. So thank you all. Okay, so I hope this video series is definitely helping you out, because it's a short time, so it's not like I need to come live every 2 hours a day, then only for 2 hours I need to teach and all. It's a single shot, so once you revise these things, then definitely you will be able to solve these questions of previous year GATE and all very easily. And definitely as soon as possible we'll also try to come up with some question series that would definitely help you out. Okay, so thank you all, we wish you very good luck, and please keep on preparing. Okay, because if you stop your preparation you will lose the connection with the subject, and definitely you'll commit blunders in the exam. So definitely don't do that. Please keep your preparation up to the mark. And since today these are the little basic things, I know I have taken the class little faster today, because majority of these things are actually the basic things. Okay, but from next time we'll definitely slow down a bit, and also we'll give each and every point some detailed explanation, like how we have given in slopes and all. Okay, so that's it from my side. Thank you all. Thank you.